Recording.
I guess we should kind of turn off some mic because of the echo.
Exactly, I think we're good. No, we should no more. You can, yeah, basically, as long as you're disconnect from your audio.
Yeah. I got it. So hopefully Massimo can hear me and see me.
I'm supposed to share.
Yeah.
So welcome back. The first speaker today is Vitas Karola, collision model algorithm for dynamics of open quantum systems application to the dynamics of supersymmetric XY/Z chains.
Thanks.
So we will be strict on time.
Okay, strict on time.
Yesterday's mistake.
All right. So I get 45 minutes. Just kidding, 30 minutes. So, so thanks for having me here. It's good to be back and see everybody. So I'm going to be talking about some work that we did, algorithm and an application of the algorithm. And it's this work that was done by two postdocs working in my group. I have a few postdocs and students, Nathan Myers and Rishka Sable. So they're currently fielding offers for postdocs right now, if you're interested. So I'm going to motivate in just one slide what we're going to talk about. So talk to me a little bit backwards. What I mean by that is I'm going to talk about a method that uses exact diagonalization, and then later on in the talk, I'm going to talk more about the motivation. So what I'm interested in is exact diagonalization, and in this slide at least, arguing why it can be useful. So normally we think about going to the thermodynamic limit, but if you think about it, ED is useful in the sense that you get all or many of the energies, so you can do dynamics exactly, so that's good. We also get wave functions, and we can compare, I guess, with the exact wave function. So when you have non-trivial, strongly correlated problems, you can test theories. I wouldn't say that that would be useful, except we have this example of the fractional quantum Hall effect, right? Where you can make strong statements at very small system sizes. Okay, so this is an example spectra. I won't be talking about FQHE for the rest of the talk, but I'm just going to show you what I mean. From ED, this is a plot of energy versus wave vector, and what this is solving exactly and plotting a whole Hilbert space for is two-dimensional electron gas projected into the lowest lambda level spinless particles, fermions on top, bosons on the bottom. And this is just an 8-particle spectra, but inside of this is more or less the entire physics of the fractional quantum Hall regime. This ground state at 0 energy is the Laughlin state for this particular truncated Coulomb model. And you can see this branch here is another important thing. It's called the Roton mode. These things have been observed experimentally. Part of Laughlin's Nobel Prize was awarded because ED was able to verify that his wave function was correct. What's also interesting about this is it's 8 particles. So in other words, if the system scales to infinite number of particles, you get the same physics. And this is because there's no like ordinary spontaneous symmetry breaking, right? You just have a topologically ordered gap state, uniform liquid, nothing else is happening except these quasi-particles at best.
What are the boundary conditions?
In this case, it's a sphere. So that's why there's only one Laughlin state. But if you puncture it and put it on the torus, then you get 3. So that's actually an important question. How many 0 energy ground states are there? It depends on the surface, which is why it calls topologically ordered state. So it's kind of why, like, the answer to that question is kind of why this is interesting, beyond which the fact that it's been observed experimentally. You get topologically ordered states. So I promise later I'll talk more about motivation, but just to get it here, I want to think about systems I can study exactly that are interesting, and by that I'll say topologically ordered or topological. And what I want to think also about, I'm interested in experiments, not just in semiconductors, but also AMO systems. They're closed typically, and we don't think of thermalization very well in that context. So I'll be talking a little bit about experiments in the sense that you would have to rely on open system dynamics to get to something that's steady state or some thermal setup. So that's part of the motivation here, is to try and intersect all these 4 ideas. And the question I want to ask is there something beyond the fractional quantum Hall effect where we don't have to care about system size in the sense this number doesn't have to be too big? So is there something like that? That's a key question. So what I'm going to do, like I said, is I'm going to give kind of a backwards talk where the beginning of the talk is a method that is implementing what's called a collisional model. What we argue is that you can do this with an ordinary metropolis method. So that's what I'm excited about, because we can take a system, finite size, and do exact diagonalization and couple it to a bath, and in real time watch it relax into thermalization. And we've come up with a method that does this so that you can scale up a little bit better than you would doing a full ED of both the bath and the system. And then the second part of the talk, I'm going to talk about a specific application of this, so you can see why we constructed the method. We're going to talk about XXE chains in a supersymmetric limit. So you think there's something interesting there. Okay, so what we're interested in first, in the first part of the talk, is kind of simplifying this hard problem, right? So you have a strongly correlated system, Hamiltonian HS, coupled to some kind of bath. And what I want to do is, in the sense of Kaldor-Leggett or these other models, you have a Hamiltonian that you actually talk about in terms of interaction. So microscopic attempt at thermalizing the system, but in dynamics. So this is obviously non-trivial because the system size scales exponentially, like the Hilbert space scales exponentially with system size, and so does the bath. And so if you try and construct the exact density matrix, so this is the wave function, so this is the whole thing, as a function of time, Tn is a time step, it would be nice to see yourself relax to the Boltzmann distribution. But this is a hard problem, right? Because, you know, we assume that's true when you have a solid, but the question is, if you have a closed system, watch it evolve. When you put it temporarily in contact with interaction, it's hard to do an ED because you have both the exponential evolution space of the bath and the system. So this is obviously non-trivial. And so the only thing I'll be doing the first part of the talk is just removing the hard Hilbert space in a certain limit associated with the bath so that we can time evolve or use exact diagonalization just on the system. So that's the aim of the protocol that we're coming up with. And so the context in which we're doing this is what's called a collisional model. It's become popular recently to study different aspects of system dynamics. And one thing people have been interested in is studying non-Markovian dynamics, issues of thermalization, and so on. So it works like this. You have a system here, S, and you turn on a Hamiltonian and you time step from one time step n to n plus 1. And in one time step, you interact with what you're calling ancilla, which is representing the bath. So the bath is drawn from a temperature. Let's say it's at inverse temperature beta. And then as time moves on, you work on your next ancilla, couple it to the system, decouple it, and repeat in that way. So you draw from the bath some ancilla. And obviously, this is, if you want to study the dynamics using exact diagonalization, this is non-trivial because the whole density matrix then needs to take a partial trace of the system density matrix times all the system time evolved unitaries, and then there's coupling and so on. It's just really non-trivial. So you can only do this, and people, when they do these studies for system sizes, just have like a couple spans because they're doing collisional model studies in a sense. Yeah.
Yeah, just wanted to ask, so it's one ancilla or it's a?
It's many repeated, and they can be anything. So you could have, if you say, let's say you have a spin chain like we do, we'll have one ancilla per site. Or sometimes people take one ancilla coming in repeatedly at the end. So collisional models are broadly done, sometimes one per site, sometimes one at the end.
But is the ancilla in a pure state or ancilla is kept?
That's a good question. And so different people are excited about the collisional model because you can do both. So you can put the ancilla in a pure state and then watch the interaction happen in real time. What we'll do is we'll draw from thermal distribution. So that's what's pretty nice about it, is that there's some tunability.
And unlike Kaldor-Leggett oscillators, it could be qubit.
It could be a qubit. So it could be, and what people are excited about, we're not going to do this in my talk, but you can entangle, these guys can be entangled. Look at this non-Markovian and memory effects. So this is an interesting model that we want to implement numerically, but the price you pay is that you have the exponential Hilbert space and ancillas and all this partial tracing and so on. So we want to get rid of that in some limit. So one way people have argued that you get thermalization is that you can take the ancillas to be a collection of modes where the frequencies match the frequencies of the system. So the bath is a collection of qubits or whatever that have frequencies that match your system. So then when they come in and collide with the system, you're drawing from what you would want is a thermal density matrix of your bath. And as time goes on, this interaction coupling strength G then tells you to make some transitions or give up some energy to the bath, and you can evolve in real time. And like I said, so folks have looked at small system sizes, and they've shown that in this setup, the bath eventually relaxes, the system relaxes to the thermal steady state, even though you're in like an initial incoherent state or even a coherent state. So this is the approach. So K and L here index energy modes and transitions in the system.
Okay, can I just ask a broad question, and if it's not relevant, if I wanted to guarantee that your subsystem thermalizes to whatever temperature, it's difficult to do it with Lindblad type thing. And
Yes.
the other standard thing is Lindblad.
Yes.
And it's like, unless it's infinite temperature, zero temperature, I don't even know like how to
Correct.
correctly evolve it. But you're saying that by doing this collisional
Yes.
thermalization, you can.
That's exactly right.
That's great.
So
Okay.
Lindblad, part of the purpose of this talk is avoiding Lindblad because there's so many technical issues and you can only use a narrow window. So using collisional model, we now know you can get the thermalization, but the price you pay is like you have to rig it so that each of these energy excitations is covered by that.
But is it rigorous or is it like empirical? Is it like Monte Carlo where you can kind of like
Yeah, it's
converge?
it's rigorous in the sense that people have shown here that this has been going on since the 60s. Okay, so yeah, but we're happy with it numerically, and we've seen it happen. So I'm just reasonably convinced that all the many-body models have studied empirically. Yeah.
Just to review. I mean, it looks like this is, on the previous slide, you showed what you really want to do. You're going to do
Yeah.
bath at some temperature, and
Yeah.
evolve it, it entangles with your system.
Yes.
So it seems like in the next slide, in this collisional model, that's what you're doing.
Yes.
So in what sense is it
Oh.
a technique?
Oh, right. Good question. So what am I doing here?
Collisional about
So
it?
we can step in real time and watch this thing thermalize
Right.
and just make sure it's happening. I kind of slipped in on thinking of AMO systems. So in one sense, do they thermalize, right? They're isolated. So what do you got to do to them to make sure and tell your experimental colleague that it's for sure thermalized? How long do you have to wait? And if you go through the transients, you need to hit a steady state. I mean, I agree, like it's kind of obvious it's going to thermalize if you have all the transitions in the bath and you're ready to go, but we want to like step through in time and just track everything.
Were you saying if there was no commensability between these transitions, it wouldn't thermalize?
Yeah, we've tested a few of those. That's right. If you start missing out on low energy states in particular, then you can get trapped in some excited state. These are many body systems, so you need to make sure you have your distribution covering all these transitions.
But on the other hand, there's ETH, and so
Yeah.
there's nothing about this that's.
Okay,
suggesting
so
it violates ETH.
yeah.
You're saying it's because it's small systems, so maybe it would take a
So
long.
right. So the question is, why am I not relying on ETH? That's the thing, because I want to study systems with a lot of symmetry, and I want to look at systems. I was going to get to motivation in the second part of the talk, right? I want to look at global order. So I want to look at global order parameters, not some kind of local order parameter. So that double whammy means I can't thermalize in general using ETH. I can't rely on ETH. I'm going to look at the XXE model right where there's all this symmetry.
Meaning you get stuck in the symmetry zone.
Exactly. So you always end up in a symmetry. I mean, we tried to do ETH. We tried to thermalize with just putting in, like you keep asking questions about all the things we tried. Try and do the thermalize with the guys on the end, but you in time and you try and eliminate some of these excitations. We need all this to thermalize for the problem I'm looking at. But you're right. So normally you would just have a big system and ETH would kick in. You know, do a local correlator. But we want to engineer a bath so that we can engineer an energy distribution. So this is kind of an example calculation similar to what's done normally in the literature. XXE chain, I'm going to pick a very symmetric point and time steps were 1. This is just two-site calculation dash line shows the collisional model thermalization dash line are the thermal density matrix elements, and you can see as time goes on, you thermalize this. That's good. We can increase
Yeah,
this.
but as a bottom line of your discussion with Leo,
Yeah.
so your title is not complete because you need to add the bat because
Yes.
you were saying that it's a chain plus bat because
Yes.
you know,
Yes.
bat is an important part of your system.
Exactly right. So XX and chain, yeah, that's correct. Plus fat. That's right. You need that. And so that's
Right.
what is evolving into the thermal state. That's exactly right. That's a good point. Yeah. We went to bigger system size. We can track all the elements in the density matrix because it's ED and just watch it thermalize. This one way to present that is through this trace distance, where you can see the difference between the thermal density matrix and the one we're getting goes to zero as time goes on. And it's hard to go beyond 4 in these exact studies with the collisional model because you need to do all this partial tracing stuff.
L is the number of sites.
Yeah, the size of the chain, yeah. So this is kind of normal and known in for collisional model folks. Then what we asked is, how can we get to bigger system sizes? So that was the method we introduced. And so our proposal was to just draw the ancilla from in a Monte Carlo sense and not have to worry about partial traces and doing all the matrix manipulations. And the question is that right? So we wanted to test this. We proposed a jump from one ion state to another and just use Monte Carlo to draw with a Boltzmann factor, and beta is now the inverse temperature of the bath. And on our Metropolis scheme, we just wanted to time evolve and do these draws and see if we can get the same answer as a collisional model. So that's the question. So in other words, we don't want to do partial trace or keep track of the inner space of the bath. We just want to time evolve the system. And we get pretty much the same answer. So this is just for a small system size again. This is the same plot, but now with the collisional model removed or replaced with Monte Carlo. So we're getting an equivalence empirically. You can see you get thermalization. So what we were able to do is prove that this equivalence is good in a certain limit. And the limit, the punchline is that if the temperature is low, this works. So you can get rid of the collisional model fast. So what we did is we did 2 calculations. One, we calculated the total density matrix as a function of time using Monte Carlo from these draws from the thermal bath. And the second one was a lowest order Dyson series expansion for the collisional model. So as you do time steps with the generic system bath coupling, you get the density matrix, and the form is the exact same as when you do it with Monte Carlo up to this constant. And this constant is different for both methods. For the Metropolis, it's just 1 over this dimension of the Hilbert spacing, energy spacings rather. And C here for the collisional model depends on the time step. Because we're doing lowest order in Dyson, you require that the time step is really short. Once you make that assertion that this constant is equal to that constant, you get a condition on what exactly tells you you can use this time evolution method for, which is in basically low temperature. So the point is, if you have a gap and your bath is at temperature below that gap, you can replace the collisional model with an ordinary common sense thing, which is drawing from a Metropolis, in a Metropolis sense, from the bath randomly. So you don't need to keep, in order to compute the density matrix as a function of time, you don't need to keep track of all the ancilla degrees of freedom. So that was, at least in this low temperature limit, we thought very useful, because then we can make stronger statements about dynamics and bigger system sizes. So beyond like 3. So that was the punchline of this method. And we tested it. So I just skipped all the calculations and how we proved the equivalence.
So, but that looks maybe it looks like Lindblad.
No, this is actually brute force putting in the time evolved density matrix. These are just steps, the systems from the bath, no Lindblad here. We just did Dyson series, for example, if you go into the
But
collisional model.
dagger what?
A dagger is just a creation operator for an excitation in the system. And this is for transition into bath. And so these are just a generic interaction between your system and bath.
You can use HI to time evolve the list to kind of try the composition.
Yeah, it's just Dyson series, just expansion.
Oh, that,
Yeah, just new Dyson series.
Yeah, but where are the B's? So I see the A's there, so like you expand the HIs.
In the bath, they end up getting absorbed into the energy of the bath. So these are the energy operators. Yeah. So this beta is for the beta of the bath, and these are the energy separations of that that are tuned to match this energy separation of the system. Yeah. We were seeing the reason we derived this is we saw the transients work out to be the same, and we're just like, oh, why? That's nice. So at short times, this works. And this is where the equivalence can be broken. So this is just a plot of this figure of merit, partition function of the bath over the size of the Hilbert space there. You can see that if the temperature is low, this number is small as you increase the system size, but it starts to break down. At high temperatures, you're accessing all these other weird transitions. Monte Carlo is missing a collisional model is keeping so there's a breakdown there. And so yeah, as time goes on, we get a trace distance between the metropolis and collisional model satisfying. So I'm going to hurry because I'm going a little slower than that. This is just the summary of the first part. We have a method to track the dynamics of the system, ignoring the bath, still pay the price that ED pays, where you have an exponential cost to study this main by model in the system. But we got rid of that. Is there any questions before I go on anymore? Great. So now hopefully you'll see why we like went to less effort. Like if you think about it now, I can thermalize a fractional quantum Hall droplet. It's kind of nice. So I've always wanted to do that. So I won't do that next, but I'm going to do something similar. So I'm going to talk about supersymmetry a little bit. So what I'm not going to talk about are high energy aspects of supersymmetry. I'm not going to talk about the effective theories of the Hubbard models. There's supersymmetry discussed in that context. I'm not going to talk about long wavelength theories. What I'm really interested in, is exact supersymmetry, and in that sense, supersymmetric quantum mechanics. It's a different way of doing quantum. You start with a matrix, let's say Q and a Servetian conjugate, and then you build a Hamiltonian as long as it's got some properties. One property is that it squares a zero. The other, and they're called supercharges. The other is that you want to build a Hamiltonian of interest, so you encode symmetries in these supercharges, and then there's your Hamiltonian, it's the anti-commutator of these two matrices. So if you do that, you can get some interesting properties coming out of your Hamiltonian. Notice I didn't talk about a potential or an interaction, it just pops out. And the question is, what do you see? So this has been known for a while. The first thing is that you can define what's called a fermion number. So I'm not going to talk about fermions and bosons. You may have heard that in the context of supersymmetry. But that's where this name for this operator comes from. F is just the fermion number. It has these commutation properties, and it tells you something important about the sectors here. There's something called the fermion parity. You can get only either even or odd parity. And it turns out another important property of these supersymmetric models is that all energies are positive. Sometimes you can get zero energy and sometimes not. And each energy level, this is critical, is degenerate, at least twofold degenerate. And they're identified through the parity here, whether or not you have F even or odd. So these define superpartners. All eigenstates are connected by this map, Q dagger Q. Notice zero energy mode, excitations, so I'm interested. What was done in the 80s by Witten is pretty remarkable, actually. So I didn't start reading this paper because I wanted to cite the string theorist, but I was interested in what he's expressing in this paper, which is more or less linear algebra. So what he pointed out is that there's a topological index, it's now called the Witten index, which is -1 of the F, is a non-local thing, right? It's a number of fermions sometimes, or it could be magnetization, F can be anything, but it has to satisfy the properties on the previous slide. And what he argued is that if you find that this index is non-zero, you're guaranteed to have at least one zero energy mode. So in other words, the Witten index here would be 1. But it can also be 0, in which case you say that, in this case, you say that supersymmetry is not broken. If there's no zero energy mode, then supersymmetry is broken. And the striking thing I found that he asserted there, which is correct, is that you can calculate the Witten index in supersymmetric theories at finite sizes, and it's valid in the thermodynamic limit. So this is shocking. So the idea is that if there is a zero energy mode, as long as you stay in that sector, it lasts as you increase the system size, implying that I can do ED scale up kind of good. So I was kind of excited by that. So question is,
So is it?
Yep.
You mean W0, W1? So like
It-
-1 to the F? I think.
Yeah, so
Even odd?
it depends on F. So, right, if this is F is even, then here it would be 1 on this case, I believe. Here W would be 0 since there's no zero energy mode. Notice this is a total trace over the whole Hilbert space. So his point is that if you have F1 and -1, it cancels,
Oh, I see.
and that's what's critical. So actually, as I'll argue, it means that you can go to arbitrary energy densities, technically.
It's only 1 and 0.
Yeah, exactly. So you can go to any energy density and still get the same number.
It seems kind of trivial because on the left you have an even number of states in each, and yeah.
Correct. It's trivial, but think about it. I didn't tell you what Q is. So that's what's amazing about this. So back when I used to live in Manhattan, Nikolai invented supersymmetry. It was in 1976, before the 80s happened. And he invented supersymmetry and came up with some models. So he did some non-interacting models. That's where this nomenclature of fermion boson came from. We now know a few non-interacting models. One is the polyparamagnet. It's found by Aronov and Kasher to be supersymmetric. Just two-dimensional particles, spin 1/2, no interaction. It's kind of amazing. All Majorana models, fermion, you've seen this fermion parity, zero energy mode, supersymmetry. But I'm not going to talk about the non-interacting case. You could. What I'm interested in is the strongly correlated history. It's sparse because it's really hard to prove that you have a supersymmetric model. Nikolai did. He had some spin models in there. Witten created famously some models relevant for high energy. He came up with his index in 82. What I want to talk about are the models created by Fenley and collaborators. He came up with a beautiful and very simple lattice fermion model, spinless system, where he was able to construct a supercharge and build a Hamiltonian and actually compute the Witten index. So in 3 minutes, I'll just kind of show our results. He then mapped it to an XXE chain. So now you can see I was kind of interested in thermalizing in a non-trivial way with a bath. This is the spectrum of that XXE chain. You can see sometimes there's a zero energy mode, depending on what sector you're in, L plus ND. ND is number of downspins, and L is the system size. So in this sector, there's a zero energy mode. And the fermion number is really the number of downspins in this model. And the model is derived to show, after this Jordan-Wigner, that there's an edge magnetic field on the ordinary XXE chain. So remarkably, the ordinary XXE chain, as long as you have the J coupling set to 1 and delta to 1, you get a supersymmetric model thanks to turning on an edge magnetic field, the edge same on it. It's kind of amazing.
So that's your parameter in the Hamiltonian, or sorry, you putting that in chain?
Fenley's telling us he can construct supercharges, which I didn't show you. They're simple for fermions. Yeah. Then you get this thing, and H has to be 0.5, and you get a supersymmetric point. So it seems like there's a point, not very robust. Turns out it is. And the other question is, how do we see anything? Just want to mention real quick, cold atoms, they realize XXE models all the time. Trout-Rydbergs, they happen to have an edge magnetic field due to something called the differential van der Waals shift. So supersymmetric XXE is actually
So this is a particular point for easy access.
yeah.
The easy access.
Exactly. Yeah.
Yeah.
Right. So at first I thought it was just gonna be 1 point. So we're gonna propose these guys go to 1 point, but it turns out it's a little more robust than that. So in order to see anything, punchline of the talk, I have 2 minutes, is that we introduced a generalization a little bit called the normalized Witten index, where any energy density is put inside the trace. This cancellation still happen. And the only criteria that we sample superpartners equally, and we have some weight as zero energy. Best example that we use is the Gibbs distribution, obviously. In that case, if we try and engineer a system-bath interaction, we can observe the Witten index. Before the Witten index is a mathematical quantity, this is technically an observable because it's got the partition function in it. So that was kind of obvious. The idea is if you measure F, count even, odd, take the difference, and you're done. And that tells you that you have a zero energy state. So you average the fermion parity, and this averaging is what gives you that denominator. We cooked up a method to do this using what we call quasi-grand canonical averaging. So on the left is ordinary grand canonical averaging. We're doing dynamics, calculating this Witten index as a function of time, and it reaches the thermal steady state that you'd expect. These are the numbers that Fenley predicted analytically. And in other words, we're taking an XXE chain, thermalizing it with a bath using Metropolis, and then you can actually see using sampling that's a little more experimentally friendly, you can move to Witten index observables, although it's a normalized Witten index. And so you can observe it at some time to be effectively thermalized. So which was pretty nice. The other thing we found, which we were surprised by, is that topological protection actually persists even though you break supersymmetry. So we're able to see that this Witten index, even though you start perturbing terms in the Hamiltonian, it doesn't change too much. The zero energy mode is the exact at 1, but it starts to lift, but nonetheless it protects you even though you perturb it. If you're away in the Witten index, there's no zero energy mode, then you don't get this protected Witten index. So these points are thermalized steady states. Yeah. Yeah, that's a good question. So the Witten index is topologically protected spectral index. It's technically equal to the Euler characteristics in this model. So for the purpose of this, it means it's non-zero when there's a zero energy mode. So principle, if I put this on different geometry and add a non-local symmetry, it'll change its value in much the same way that Laplace state changes its degeneracy. So it's also topological in the sense of Majorana chains, same quantity actually. And it's protected, we found, in a arguably more trivial way to answer your question. If there's a zero energy mode, we found that just doing a simpler Taylor expansion, this quantity is exponentially sort of flattened here as a function of temperature. So this is the gap. So we do a simple Taylor expansion when there's no zero energy mode. Thing's not really protected. So this supersymmetric point has to be met, but you can perturb away from it just from a simple vacuum to gap. So the gap is an equivalent, in my sense, of the topological protection. So this was something we thought that could in principle be observed, and it takes a mathematical quantity and turns it into a histogram, which. Okay, that's
Thank you very much. Good question while we are setting up your talk. No, thank you very much. We need some help.
Yeah.
Okay, the next speaker is Pradeep Katel, over screen quantum impurity at the age of a 1D superconducting hole.
Thank you. Thank you everyone for coming on Sunday morning, and thank you Vadim for giving this opportunity to talk here.
It's Saturday. Still
Oh,
Saturday.
sorry, Saturday, yeah. Well, yeah, it's 3 days long.
You want to hide those floating things?
Uh,
You click here, it says hide those. Doesn't give you the option.
Fine.
Good enough.
All right. So today I'm going to talk to you about over-screen quantum impurity at the edge of one-dimensional superconducting bulk. This is the work I did with Abhay Zakhanov, who is in the audience, and Andre at Rutgers. And I'm currently an exchange student at Flatiron, working with Miles and Tensor Network. So the work is based on this archive, which was posted just 2 days ago. So the motivation for this work is that in present days, there has been experimental observation of this bound state near superconductors, which were first theoretically studied by Yu, Siva, and Rosanov in the 60s. And after that, there has been a lot of studies on both the effect of superconductivity on impurity and effect of impurity on superconductor. This subgap states that appear in superconductor like the Yu, Siva, Rosanov state, Majorana zero mode, and then Henry bound state, which appear in the interface between the normal metal and superconductor, are quite resilient to different kind of perturbation. So this makes this mid-gap state a potential candidate for qubit. But the problem is that most of these theoretical studies have been done in semi-classical BCS superconductor. So I wanted to ask whether this state survive in strong quantum fluctuation. So I'm going to look at one-dimensional model where the quantum fluctuation is really large and try to see if this survive. And also this thing have been theoretically been studied in some Dirac metal. There have been study of SIVA study in Dirac metal. And more recently in particle physics community, people have been asking if you have quark matter made up of some light quark, and then if there is a single large massive top quark, let's say, how does this appear in QCD? And yeah.
Can you just say a word about point two, like all these appear, they're the same thing, different things, like what do you need to know, Andreev versus Majorana? Or they're all just synonyms or what?
No, I mean, Majorana zero mode, for example, and let's say Kita superconductor. And
That I understand.
yeah, so this Usiba-Rosinov states are mostly studied in BCS superconductor. If you put some impurity and do semi-classical analysis, it appears as a mid-gap state, not a zero energy, but mid-gap state. The Henry bound mode are also mid-gap state that appear in, like, if you take a normal metal or a superconductor and do a study of the interface, then they appear as this.
So different ones appear depending on. the
Yeah,
type
yeah,
of interface,
yeah.
but they're not the same.
They're not the same. So on the mathematical side, we know now Kondo impurity is studied as, can we describe it 1 + 1D defect operator and 0 + 1D defect operator in 1 + 1D conformal field theory. And this triggers RZ flow in the boundary, which goes from UV to IR, which is characterized by something called this Z function. It is more like a C function in the bulk of a CFT, but it is only in the boundary, so called Z function. I'm going to describe about this in a bit. And I want to ask the question, like, what happens when the bulk is no longer CFT and opens a gap? When you have the cutoff in the IR spectrum, how does the boundary RZ flow gets affected by this? So in order to study this, I'm going to look at one-dimensional model where I'm going to have fermions in the bulk. So in the bulk, the fermions are two flavor, left and right mover, and then they have three color index, spin, let's say 1, -1, and 0. And then they attractively interact in the bulk with spin density and charge density interaction. And in the boundary, there is a spin half impurity. And when the bulk fermion scatter of the spin half impurity, it changes the chirality. So this model, when you set J equals to 0, was solved by writing this spin 1 operator as O3 by Nathan and his postdoc in 84. And if you now set Z equals to 0 and look at only J, this was solved by Alexey and Paul Wigman as a model of, in their excellent review, a multi-channel Kondo problem. This appears as a two-channel Kondo problem. So I'm just going to stick these two non-field theories, one in the boundary of another, and try to solve it together. So in this problem, both G and J are running coupling constant, but I'm going to show you that exists a RZ invariant quantity D, which is a function of G and J. And using this RZ invariant quantity, I'm going to characterize the boundary phases. So if you stare at the Hamiltonian, there are a lot of continuous symmetry. For example, there is charge conservation, there is U1 chiral symmetry, there is SE2 spin rotation symmetry. But I'm going to describe this as a superconductor, so that means it opens a gap in the bulk. And as we are in one dimension, we cannot break any of this continuous symmetry, so there has to be one a discrete symmetry. Yeah.
Just notation, what is RNS? Sorry.
RNS are the spin index, 1, -1, 0 for here.
Okay, spin 1.
Yeah, this is a spin 1 fermion interacting with spin half impurity in the boundary.
That's the always clean.
Yeah. So I'm just going to briefly write this fermionic model in terms of Majorana. And if you look at the Lagrangian, so this is the Lagrangian. You have two flavor of Majorana and the spin index 1, 2, 3. You can momentarily take this for n to do Larsen analysis. And if you define this fermionic bilinear, the Lagrangian just becomes R square plus R twiddle square. And now you can see a discrete symmetry here, which I'm going to call the chiral conjugation symmetry, which is R going to R twiddle. And this is the discrete symmetry that is broken, which you can see if you do Lassonde analysis. So this is dynamically broken where you have two kind of vacua. In one, you have the R square that gets the expectation value, whereas R twiddle doesn't. And if you look at the conjugated vacuum, then the R twiddle gets the expectation value, whereas R doesn't. And
Excuse me, I missed it. So Fernand's what spin do they carry?
the fermion in the bulk are spin one.
Spin one.
Yeah, so you can write it as the O3 model, and this is the O3 symmetry. So basically this has some O2 cross O2 symmetry, and that's the O2 cross O2 symmetry that we are looking at, and that's why the model supports the kink excitation. And basically all I wanted to point out is that this is the mechanism by which it gets masked. The discrete conjugation symmetry is broken. So now back to the full model with bulk and boundary. So if you look at the problem and study the scattering matrices, basically all the scattering matrices in the bulk satisfy this Breding relation, so-called Yang-Baxter equation. And in the boundary, when the fermion scatters off the impurity, it satisfies a similar algebraic relation called reflection algebra. And this together guarantees that the model is integrable. And the only point that I want to make here is that this equation says that during any scattering processes, the model doesn't create or annihilate particles. So the number of particles are going to be fixed. And hence I can basically write down, so I can translate the problem of diagonalizing this Hamiltonian into self-consistently solving these two sets of algebraic equations, where this n is a fixed number of fermion I'm starting with, and the kz are the momentum in a line of length L, and this lambda are so-called spin rapidity. So the momentums are related to this spin rapidity, where spin rapidity satisfies this couple algebraic equation. And here, this B is the bulk running coupling constant 1/2z, and this D combines the bulk and boundary running coupling constant and gives as the invariant quantity. So here, this momenta are not in a Wilsonian cutoff scheme, meaning that these are the UV cutoff is not imposed to just the non-interacting part, but it is imposed on the fully interacting momenta. And when you solve this equation self-consistently, you can derive the weak coupling RZ non-perturbatively and exactly. And this is what you see for the bulk and boundary. So in the bulk, it always flows to the strong coupling and opens the mass gap. But in the boundary, depending on the value of the bulk and boundary coupling, it could switch sign. So the depending on these two parameters, the bulk coupling could be relevant or irrelevant. Yeah.
Just clarification of your notation. So last term is the boundary term, although you have it under the integral side. But the,
Oh yeah, there is a delta of 0. So
well,
this,
there should be one, there isn't.
I mean, that is written in by specifying the space coordinate.
Right, so it shouldn't be under the integral, right? But anyway, let me ask.
Yeah, I mean, there is a delta function of 0. But, yeah.
All right, just clarify notation.
Uh-huh.
Right? But the previous term, is that, given the confusion of the last point?
Right.
Is the previous term also a boundary or bulk?
No, this is the bulk interaction. So this is x coordinate here, and this is
Okay.
x equals to 0.
Okay, so it's integrable even with interactions.
Yes, these are like the family of Gross-Naveau model, which are integrable in the bulk. And then in the boundary, it's a Kondo term, which is also integrable. So those were separately studied like 40 years ago.
And with both, they're integrable.
Yes. So. Okay, and so the D are the lines that you are seeing constant here. So if you stare at this as the equation flow, you will see that if Z is bigger, then the boundary flow actually goes back and goes to 0. Whereas if it is, if J is bigger, then they flow outward, just like in the usual Kondo problem. So you can already sense that there is going to be boundary phase transition from this RZ plot. And now when you solve this equation, you actually see that there are 4 different boundary phases. And let me describe that. So in the bulk, it opens a mass gap. And then now if you look at that first term, which is the term with boundary parameter, this one. So this D takes either purely real or purely imaginary value. So when this D becomes purely imaginary and bigger than 1/2, it sends some sign here. And because of that, there appears this new solution of this equation. And this new solution appears in a lot of these integrable models with the boundary. and they appear as like a pole of a dressed S matrix of the boundary scattering, and they describe a boundary bound mode. Now, when this boundary bound mode doesn't appear, meaning when D is purely real or imaginary, purely imaginary between 0 and 1/2, the model, the impurity is overspin by multi-particle Kondo cloud. And as we go from like 1/2 to 1, then we have this new solution. This new solution has 0 energy here, whereas the ground state is still multi-particle Kondo screen. So this two solution in both of these two state, the impurity is screen. And as we go above that, now in the ground state impurity is no longer screen, but you have this mid-gap state, and in this mid-gap state, the impurity is screen. So this is analog of the UC-Borosinov state in the semi-classical superconductor. So that appears only in this small window. And as you now go above 2, then the impurity is no longer screen. This is where the sign of the boundary coupling in the RZ switches, and it almost behaves as if the coupling is ferromagnetic. So the boundary coupling is irrelevant. And now, as I told you that this is over-screen Kondo, so to do that, I'm going to do some finite temperature. So let me briefly go through some finite temperature field theory with boundary. So when there is no boundary, let's say you have a field theory defined on this ring, then the partition function lives in a torus where the small radii is the temperature 1/beta, and you can write down the thermodynamics partition function, free energy and entropy. And similarly, when you have a boundary on a line, you have to specify the boundary condition, and now your field theory, the partition function lives in this cylinder where the colored blue and red ones are the boundary condition, and you can write down the partition function, write down the free energy, which are now 3 terms, the bulk one, and then the 2 boundary terms. So what I'm going to be interested in is this boundary free energy due to them, the impurity. Now you can look at this partition function in 2 different ways. One, by viewing your field theory living in this line and time evolution along the circumference, and you can write down the partition function in this way. Or you could view it in this way, where your field theory lives in the ring, and then the time evolution is along the length of the cylinder. And then this boundary condition become boundary states, and you can write down the partition function as time evolving from this boundary state to another boundary state. And the overlap between the ground state and this boundary state is what is called the Z function. And the log of Z function is what gives you the boundary entropy. And now this boundary state are well classified in a lot of 2D quantum field theory. For example, for the conformal field theory, these are known as the Cardi state. And also for integrable model, if you know all of the conserved charges, so let's say you have a transfer matrix, and by taking the various log derivative of those, you get all the conserved charges. So these states are special, that these are just annihilated by the odd conserved charges and not by the even. But in this problem, I cannot quite do that because the integrable model is with Kondo impurity in the edges, so I don't know how to do all of this classification and find the boundary state. But because this is a universal quantity, I can obtain it by doing thermodynamic, by first finding the free energy and then finding the boundary entropy. So the exponential of boundary entropy will be this Z function. So what I'm going to do is I'm going to calculate the thermodynamics of this problem first with impurity and then without impurity, and take the difference of the free energy and calculate the boundary entropy. So skipping all the details, what goes into here. So the thermodynamics is given by this horrible recursion relation in terms of this eta, where this Z and this N are the integral operator. And then you need 2 boundary conditions. One boundary condition is specified at 0, one at infinity. And with this, your boundary free energy, which is the impurity free energy, is given by this function eta 1. So when you solve this equation and find eta 1, you can find the impurity entropy. And the impurity entropy looks like this. So at low temperature, there is an analytic expression which shows that it is a function of m beta. And the interesting thing here is that at zero temperature, it has residual entropy of log square root 2, which shows that it has the same universality class as the two-channel Kondo problem. And then in the high temperature, it is on the screen as the impurity entropy goes to log 2. So basically, with this, toward the end, the summary is that I looked at this problem with spin 1 fermion in the bulk attractively interacting with charge and spin density. And in the boundary, there is Kondo impurity. And I solved it for all values of J's and Z that are positive, and found that the Kondo phase, which would exist everywhere in the parametric regime if there were no bulk interaction, is now shrunk to a very small parametric regime. Similarly, the YSR regime, which would exist throughout parametric regime in a BCS superconductor, is now restricted to only small parameter regime because of strong quantum fluctuation. And then because of the strong bulk interaction, there is a parametric regime where impurity cannot be screened. It is as if the boundary coupling were ferromagnetic.
Excuse me. Looking at your formula for the boundary entropy, I see that at t equals 0 is always log of square root of 2.
Yeah.
Always.
No, but I'm only looking at the Kondo phase. This entropy is only for this regime, not here.
For this reason.
Yeah.
And then what happens for the other?
So there is a lot of thing in the literature going on how to do thermodynamics with this boundary spring present, and it's not settled yet using the traditional thermodynamic wet answer, but there has been this recent progress with what is known as this transfer matrix method, and I haven't quite looked at those.
Okay.
Yes, I have a couple of questions. So one is, can you comment on, just not familiar, my own ignorance, like how to do this marriage of techniques? On one hand, exact solutions,
Yeah.
the ansatz, and the other hand, RG. So you show some RG flows.
Oh,
Is
so-
that through bosonization?
No. These are RG flow derived from within beta answer, but
So how is that done?
so I mean, basically, so you're looking at this field theory, and the only problem here is that I'm not in Wilsonian cutoff scheme, which is the cutoff scheme imposed in just the non-interacting part. So I'm imposing cutoff in entirely interacting field theory. So my momentum cutoff are the interacting momenta, but within that scheme from beta answer, I can find, let's say, so first,
Or you have cutoff on rapidities or something, or?
yeah.
I see it at the
I
exact
mean,
level.
yeah, so I mean, first it's done with this Bayer parameter, and you have to put scaling limit to find this bulk RG parameter, which is the mass cap. And then like you can invert this relation to obtain the RG relation. But this RG equation, again, if you do for Kondo, for example, from beta answer, this is what you get for Kondo, which is one loop exact in this language because of a different cutoff scheme. But of course, in other Wilsonian cutoff scheme, it has like other terms like the,
But
yeah.
how do you extract G from the solving for the rapidity? How do you go back to G just to see it?
You mean,
I mean, you solve the beta ansatz equation, you get all the lambdas.
Yes.
But at the end of the day, what you want to establish the RG equation is just one beta function of one.
oh, sorry. Oh, sorry. The Z has two, sorry, I'm using the same thing. The Z, this is the coupling, but the Z that I was talking about was what is known as the Z function in CFT, which is what characterizes the UV flow from IR, the flow from UV to IR in the boundary.
That's some cosine?
That's the log of Z is the boundary entropy or the entropy of the impurity. So I wanted that, that
okay,
G.
okay.
That's, sorry,
Okay.
yeah.
G.
Two
So you
different.
do it through the entropy.
Yeah, I'm calculating the thermodynamic beta.
Okay.
Yeah.
Also, your phase diagram is in terms of these beta ansatz parameters?
No, this B is RG invariant quantity that combines the bulk and boundary, because in the bulk, sorry, in the Bayer, if you look at this, both this Z and Z are running coupling constant, but these are just these lines along this which are invariant under RG. So these are lines of constant thing, and these are the D. So I'm parameterizing by this D.
I see, it's like a circle through that.
Yeah, exactly.
I see.
Yeah.
Right, So if you give it J and G, you know. where
You know,
are.
you know what regime you're in. All right, I have
Thank you
just
very much.
one more slide.
Oh.
If you are looking for postdoc, here's an excellent candidate. If you don't like this field theory mumbo jumbo, I do some tensor network, some monitor dynamics and other things too. So here is my email.
We have some time, so if there are extra questions or postdoc applications.
I'll ask one more question.
Yeah.
So can you just comment on you had this complementary way of, doing, evolution in time
Oh.
versus transfer matrix?
Yeah, so the problem.
What is the pros and cons of one or the other?
I mean, the problem with this one is you need to know what this boundary state is. And if it is a complicated field theory, you don't know what it is. It is only known for conformal field theory or integrable models where you know how to write conserved charges. But with Condor, we don't know how to write the conserved charges. It's only at one point, and because of lack of symmetry, we don't know how to write all the conserved charges. But these are just, for example, for sine Gordon, I could write down what this B is, and then I could do it using both methods, just to show that this is a universal function I could get in many different ways. I mean, for example, in Ising CFT, I could calculate this using thermodynamics or using even entanglement entropy and so on. So it's just a very universal quantity that characterizes boundary phenomena.
But you need this BA state for both methods or not?
No, I mean, I could also get the entropy of the boundary like I did using thermodynamics, and then it is just the log of Z will give me this boundary entropy. So both methods have been like masked in problem that you can do.
Okay, thank you very much.
So I already connected to the Zoom. I don't know if this is something we have done. So that's all. It's the right way to do it. Yes, it's true. I need to connect to something. Yes, where's the table? Oh, no, it's automatically there. Okay, great. Just share. Okay, I want to. Okay, well, it looks good. Anybody has a pointer? Oh, the real old-fashioned solid state one.
If you want to have a laser, if you want a laser pointer.
No, that's good. I like that.
The next
I can
speaker,
also.
Yeah, if I have to make questions.
next speaker is Antoine George. What do we know on December the 7th about the 2D Hammond model? This.
Okay, thank you very much. So actually, as you will see, we know quite a bit at this point, and it's going to be a little challenging to summarize that in 30 minutes, but I'll probably skip over some of the slides. First thing, so really, for those of you who know Jean-Luc Godard, this is really what the title should be, because well, we know a lot, but I'm not going to be able to review everything. Okay, before I start, I want to thank many people with whom I had the pleasure to collaborate on the 2D Hubbard model. I'm assuming everybody here is familiar with the Hubbard model, so I'm only going to talk about fermions. So I'm not going to waste my time re-explaining what the Hamiltonian of the model is. The main message is really that there's been a lot of recent progress in our understanding, thanks in particular to what I like to call multi-method computational studies that put together different computational techniques, very complementary to one another, and also algorithmic and conceptual progress, especially handshake between zero temperature and finite temperature methods, which I described a little bit more in detail. There's been some nice recent reviews. One is co-authored by or coordinated by Emmanuel, who is here in the room. Also some lectures if you're interested on my Collège de France website. But this is 2021, and in fact, what I try to convince you about is that there's been even quite a bit of progress since then. So the field is moving. In particular, I will focus part of the talk on two recent papers one about superconductivity that appeared in Science like 6 months ago, and another one on the pseudogap that appeared also in Science a few months ago. And maybe this is a tribute to Boris, because I believe this is the first diagrammatic Monte Carlo paper that made its way to Science. So that's a tribute to Boris and Nico. Okay, so what do we want to understand? We want to understand the nature of the ground state. We want to understand whether it has long-range orders and of which type. Note that in 2 dimensions, the Mermin-Wagner theorem, the strong fluctuations prevent ordering at finite temperature for a continuous symmetry. So that makes for really interesting crossovers as a function of temperature as the correlation length of some of these orders grow. And of course, ultimately we want to understand response functions and connect to experiments. So what I'm going to do is I'm going to give you a little glimpse into completely non-technical about the sort of range of computational methods that are available these days. Then I'll move on to ground state properties. Then I will say a few things about the pseudogap. And finally, I will try to connect the different ends of this. So let me start with a glimpse into computational methods. Well, this is one way I like to describe the overall landscape of computational methods. If you think about 2 axes, temperature, energy, and coupling, there are really some methods that start from here. So basically start from the ground state. And one thing I want to emphasize is that computational methods are not a black box. Okay? They are not just simulating nature. They actually rely on concepts. Okay? So every single method comes with a certain way of looking at the system. And so those methods start with the wave function. And the challenge there is, because the wave function is an enormous object, blah, 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 we all know that. The challenge is how can we compress the wave function in an efficient way? And so one of the very successful methods to do that, and Miles is hiding behind the pillar here that is in the room, is matrix product states on which you can act with tensor networks. And that has been a super successful approach, especially in quasi-1D system, using a variation algorithm called DMRG. And the concept or the organizing principle behind the possibility, the efficiency of MPS compression is entanglement, or rather the low level of entanglement of certain wave functions. By the way, there's an emerging new type of compression which is using neural network encoding of wave functions, the so-called neural quantum states. And there is quite a bit of progress on this for fermions as well, but I'm not going to talk about this in this talk. So that's one class of methods. And up to relatively recently, these methods were confined to 0 temperature. On the other hand, we have another class of methods, and there are some experts in the room, which we like to call embedding methods. A poster child from this is Dalrymple mean field theory, but also all its extensions using clusters, for example, or vertex extensions. And those methods leverage on a different concept, and that concept is the concept of locality. If you go at high temperature, the correlation length for all the various incipient orders are small, so things are quite local, and you should be able to leverage on that computation. So that's what embedding methods do. And so by looking at the situation like this, you immediately see that there is a sort of gap between those methods that come from high energy, high temperature, and work when the correlation lengths are somewhat small, and those methods that were confined to 0 temperature. And a lot of the interesting physics is happening here. So obviously we need some sort of handshake between these methods. And one of the really interesting developments in the recent years is that this handshake has become possible. First, because computational possibilities have allowed to go down in energy scale or temperature in the embedding methods. But importantly, also because these compression methods based on MPS have now been extended to finite temperature, combining those ideas with sampling. And that's the minimally entangled typical thermal state method that I will mention later in the talk. So this makes for interesting handshake between these things. And last but certainly not least, we've witnessed the appearance of other types of methods which address the problem differently. Perhaps you may want to think of diagrammatic Monte Carlo as working along this axis, so generating terms in the perturbation theory in U and trying to resum them the best you can. These methods are finite temperature methods. They work as long as the perturbative series at finite temperature converges, or rather within the radius of convergence of those methods. But it turns out that when coalition lengths, again, are not too large, these methods, even though they generate terms in the perturbative series, allow to reach non-perturbative effects, or at least enter into strong coupling regime. Perhaps that's a better way to say that. And of course, these were pioneered by Nicolai and Liboris many years ago and have been sort of transformed for fermions by ideas based on connected determinant methods, Riccardo Rossi, etc. Okay, so this was a sort of pitch more than a presentation of the different computational methods that we have at hand. And by putting all these things together and even using some ideas of one method into another, we've seen a culture of multi-method collaborations that has appeared. Again, Emmanuel played a big role in this, and especially the Simons collaboration promoted that culture, and we are strongly trying to continue that culture at CCQ next week. This is a bunch of papers, but there are many others. Okay, so this being said, I'm going to try first to tell you what we know today on December 7, 2024, at least what I know, about the ground state. And this is what we know. Of course, oops, I don't know why this is here. It shouldn't be here. Yeah, maybe it should be here. So we know that from mean field, just Hartree thought, right? Hartree thought would tell you that the phase diagram of the Hubbard model has first some, well, Hartree thought would tell you some spin ordering, but of course we know Mermin-Wagner exists, so this cannot be ordering. This can be generously interpreted as the growth of some sort of spin correlations, but Hartree thought would also tell you that at low temperature, eventually things creates tri-p charge patterns. And this has been confirmed using all sorts of numerical methods. This is an auxiliary field Monte Carlo phase diagram at 0 temperature of the ground state of the Hubbard model with no T prime. T prime is the hopping along the diagonal of the square. So when there is no T prime, the ground state phase diagram is widely believed to have two phases. I'll come back to superconductivity in a minute. A phase here at low doping, which has both charge and spin ordering, the so-called stripes, and a phase here which has no spin or charge order and perhaps some very, very low eventual Kohn-Luttinger instability to superconductivity that have to take place, but I'm not drawing this on this. But then please pay attention to that black line here, which separates these two regions. I will come back to it in the rest of the talk.
Can I ask about
Yes.
insulating phases there, like a commensurate fillings?
So this is actually an interesting question as to what is the nature of the stripe, depending on the commensurability or not of filling. I don't think this has been completely nailed down at this point. When T prime is 0, what you get is, for certain fillings at least, is the so-called filled stripe, okay, which would have a situation like this, where the spin wavelength is twice the charge wavelength. So basically, this is the sort of canonical picture of a stripe where you have a spin density wave with a certain wave vector, which is different from pi and directly related to doping. And the charge the hole likes to be located at the node of the, that's the whole density at the node of the SDW, okay? in that case, there is one hole per site there, right?
Right.
But if you have a fractional filling of the hole, then you get a metallic phase.
But at zero doping, you have an interferometric, you just didn't.
Yes, at zero, I didn't say that.
Yeah, okay.
Yes, at zero doping, everything is understood. There are interesting crossovers.
And this is 2D, right?
This is 2D, yes. Yes. Forgot to mention that.
Just want to make sure that.
Yeah, no, absolutely. Okay, one thing which is important to realize, oops, sorry about that, is that all computational methods, and I really insist on all, agree that leaving aside superconductivity for a minute, the low doping ground state has to have charge and spin order, has to have sprightly order. Even dynamical mean field theory.
Excuse me, this,
Yes.
this 1/4% means it is just an instrument.
Yes, for that specific pattern, yes, that's correct. Even dynamical mean field theory, if you do it, single side dynamical mean field theory, if you do it in an unrestricted way, leaving all sides do whatever they want on a finite size system, which you can take very big if you do single side in P, will tell you that there are strokes. They're very nice papers, not so well known. This paper is not good. Okay, so now what about superconductivity, which is really all you guys probably care about. So this paper appeared, I'm not involved in this work, this paper appeared about 4 years ago. And the title was Absence of Superconductivity in the Pure means T prime equals 0, two-dimensional Hubbard model. And so that paper would let you think that actually the phase diagram is really this, T prime equals 0. So spin charge stripes, we can describe exact nature, and no spin charge stripe, but no superconductivity. Well, why is this question difficult? So the question is difficult because everybody agrees, all the methods, basically, including especially embedding methods, agree that there is a tendency to pairing. So what does that mean? This means that if you actually put a little D-wave pairing field on top of the Hamiltonian, you will find a range of doping where there is a strong response. So this is an example of what you measure versus the pairing field. This is not a magnetic field. This is conjugate to the D-wave pairing order parameter. And you see there is a region of doping here, a dome-like shape, where the system has strong response. But this is not enough, of course, to document that the ground state has superconductivity. What you want to do is compare the energy of that state to the stripe phase in the limit where there is no applied field. And it's been realized that these energy differences are extremely, extremely small. So they are on the scale of hopping over 100. So it's an extremely difficult game to actually decide who wins in the end. Of course, there are many, many things that will eventually possibly destroy the stripe ordering, especially the nearest neighbor V and so on, okay? And so I think it's enough to a large extent to be confident that the 2D Hubbard model plus epsilon other terms has what it takes to reproduce superconductivity in systems like Q-trace. But if you really want to nail down the Hubbard model, you have to confront that question. Yes, Victor?
Yeah. First of all, are you only studying model, Hubbard model without prime?
No, T prime will come if I have the time.
Okay, and the second question, you did mention, well, it's maybe a silly question. So, silicon lecture,
Yeah.
Should I think about this being in lecture?
No. No, you can't think about this as being co-integer because the scales are very large. So you see here that the other parameters are
I would say
Are much larger.
by definition because the Fermi surface is absent. The moment you have stripes, you do not have Fermi surface.
yeah, but yes, but okay, yes and no, because the question you raise is whether the superconductivity and the stripes coexist.
Oh, that's a separate question.
Well, I mean, if there is uniform superconductivity with no charge ordering, right, then the state above that is not necessarily gonna have
There
stripe
are two
correlation.
separate questions. Convergence mechanism for
Yeah.
uniform superconductivity and superconductivity on top of stripes.
Yeah.
Those are kind of apples and oranges.
Yeah, I agree. I agree. But what I'm saying is that if the the reason I answered that is because if the superconductivity is uniform, right?
All right.
Above the KT transition, let's say, there is at low doping, there is a pseudo gap Fermi surface, but there is still a Fermi surface. I mean, it may be truncated, but there is still a Fermi surface. Okay. So this is a very difficult question, and the authors of this paper that I just showed went out of their way to resolve this question, combining different methods, tensor networks, AFQMC, and so on, and they concluded for the absence of superconductivity and the charge stripes always winning. But if you look carefully at the paper, you will realize that there are certain points, certain regions of coupling. I haven't shown the points that were studied for superconductivity here on this phase diagram, but which are not really present in the paper. So it could still be that near this boundary, there is still room for superconductivity for T prime equals 0, in my opinion. But by and large,
What is the order of the transition between green and pink?
I don't think this is known and so well, in fact. And in fact, neither that transition nor the thermal transition as a function of temperature into the stripe phase is very well understood. I'll show something about this later.
So is the pink region just Fermi liquid? Is that how it should work?
Pink region is well, that's an open problem.
Well,
Mostly, yes.
Doesn't look anomalous?
Well, mostly yes, but whether there is a region where the metal in that pink region at finite temperature is a strange metal, I think is an open problem in the 2D above. That's one of the open
But
problems.
it's metallic.
Avishkar, it's metal, yes. Avishkar will tell you need this order to account for the strange. I think he will tell you, he has a right. Okay. So crucial role of T prime. So somebody wanted to hear about T prime. This is T prime. It's been known from many studies using the embedding methods, cluster DMFT and so on, that T prime promotes superconductivity. And this is one example on sort of ladder systems, but there is a recent paper that's one of the two science papers I just showed of this year that has now nailed this down using again a combination of tensor networks and AFQMC. And so what these people show now is that this competition between stripes and superconductivity is now winning competition for superconductivity in the presence of T prime. And so these are a few data points that they took where they can demonstrate that there is a pairing order parameter that survives and that the state is superconducting in the limit of zero pairing field. However, this state here and here also has coexisting very weak, but coexisting charge modulation. I didn't put a slide for that, but you should know that. Whether this evolves at larger doping into homogeneous superconductivity has not been yet studied, or a larger T prime.
And T prime is reasonable numbers compared to.
Yes, reasonable. Yeah, I think in this paper, T prime was maybe 0.15, something like this. One should, of course, continue these studies up to 0.3, which is more typical for the highest TC superconductors. But yes.
And should I take this as a kind of evidence of pair density wave? You were saying this is.
I'm not sure about pair density wave. There is a charge modulation.
Well, so that'll reduce.
So
I mean, just I guess trivially, it will reduce modulation and then.
Yeah,
Yeah.
in the pair field. Okay. Yes. So now, okay. So actually, in answer to Boris' question, maybe this question is to a very large extent not so well understood. Mermin Wagner tells us that if you start from the stripe phase and you hit up, you lose spin ordering immediately, but the charge ordering should remain because it's a discrete symmetry. However, imagine you are at 1/8 doping, this discrete symmetry is Z8, right? And we know that a Z8 clock model can have a KT transition despite the discreteness of the order parameter. So In fact, there is only 2 or 3 papers in the literature that have ever really asked this question. And on the computation side, I only know one, which is one I co-authored recently with Shiwei and postdoc with now at ORNL, Boshao, where we say in that paper that there is a clear evidence for a finite TC for the charge ordering, but the numerics is not to the point where we can identify the universality class of this transition. So this is an open problem. Okay. So I mentioned the METS method, and I also want to tell you that in the spirit of this sort of handshake, the evolution from stripe order at low T to a state with strong antiferromagnetic pi-pi centered correlations at high T has now been mapped out, certainly in restricted geometries allowed by METS. Thanks to this method. And this is a paper that Alex Vipek was the leading force behind, but I co-authored this with Miles and with Steve White. I don't have too much time to tell you what the METS method is. Basically, the idea is you start from a product state, you imaginary time evolve it to beta over 2. At each step, you actually use an MPS decomposition and to do a time evolution, and then you sample over the original product state you pick. And so what you see here is the magnetic stuff. So this is done on cylinders, okay, of about 4 in diameter, which admittedly is not very large, and 16 in length, so 64 sides. And so but you still see interesting physics, and this is what you see. This is the magnetic structure factor, and this is the charge structure factor. And so what you see as a function of temperature is that this is the spin structure factor at pi-pi in blue. So you see that there is an onset of pi-pi centered spin correlation at fairly high T. And for a while, the pi-pi spin correlations dominate. And this is completely consistent with what we've seen for many, many years in clustered MFT studies. So the spins run the show. That's the important message. And it starts at pi-pi. And then at some point, you see that the pi minus doping of pi-pi correlation. So the SDW takes over right here. And at the same time, the charge kicks in. So in other words, there is a high temperature regime in which the charge does nothing. And the response is entirely pi-pi growing correlation length. Okay? And then at a lower temperature, the charge and the spin start talking to each other, the charge reacts, and you get into, in the infinite system, most likely the charge phase transition, right? So this is what's going on. And this is completely consistent with what cluster embedding methods have been seeing. So this is what I like in sort of.
So this is right, right?
Eventually, this is right, yes. Yes.
Antoine, if you increase temperature, can you think of it as an ordered by disorder going this way? Ordered by disorder, increasing temperature.
Why order by disorder?
So sometimes people will say that when you increase.
No, I know that, but why is the why?
So the peak is just going up.
Oh, you mean no? It's, I think I'm not sure I would think of it about it like this. I think, or because you are saying this increase.
Yeah. Okay.
I have to think about that. I think it's more a gradual shifting of the yeah. Okay, so I have minus 3 minutes to tell you a bit about the pseudo gap. So I will still tell you a couple of things. Can I use 5 minutes? So
You still have them?
I have them. Okay, so I use the ones I have. There's a few more.
Wow.
Okay, no, but I try to think. So let me tell you a few things about the pseudo gap. So it's very tempting, to say, actually, this regime here, where the pi-pi correlations grow, but the charge hasn't done anything yet, this is actually the pseudo gap regime. So what do we know about this? So let me first remind you what we call the pseudo gap. So the pseudo gap was discovered experimentally as a loss of density of states from NMR, okay? And Arpes quickly jumped in and allowed to realize that this loss of density of states is associated with the antinode of the Fermi surface, while at the node there is still a reasonable quasi-particle. Okay, so this is the pseudogap phenomenon. It's a crossover. Okay, and in weak coupling, this is something that is sometimes a bit forgotten, but in weak coupling, there is an established theory of the pseudogap that everybody who knows about it agree on. Okay. So there is a weak coupling mechanism, which was in particular worked out by Wilk and Tremblay many years ago, and that say that roughly when the antiferromagnetic correlation length becomes larger than the de Broglie thermal wavelength, then at the hotspots, which is the intersection of the Fermi surface with the antiferroturbulent zone, you basically destroy quasi-particles and you open a pseudogap. But you should look at this criterion. This criterion, if you think about it, for the doped system, as you go to low temperature, right, this correlation length is, at least at large enough doping, not going to diverge, right? And so this should tell you that the pseudogap disappears at some low temperature at some point, okay, which is not what we see in computation. So at strong coupling, something more interesting must actually occur. I'm going to jump over this. This weak coupling mechanism has been completely nailed down and tested in computational methods as well. I'll skip over that. So what do we know about strong coupling? So let me show you another example of handshake. So this is a work we did with Wei Wu several years ago, and Michel Ferrero and Genia Kozik, which puts together two methods. Diagrammatic Monte Carlo, this was a little before CDET, so this is the historical diagrammatic Monte Carlo for fermions, and cluster extension of DMFT in the flavor of DCA, the dynamical cluster approximation. What we showed in this plot here, which is the imaginary part of the self-energy at the first Matsubara frequency versus momentum along this part in the Brillouin zone. What you see here is the purple line being diagrammatic Monte Carlo, and the squares being DCA extrapolated to very large cluster size, including 64. These are the parameters that made this possible. You can't do that, unfortunately, everywhere. And you see that there is excellent agreement between these two methods. So one can say here that one has nailed down the self-energy of the Hubbard model to good precision. And you see that this imaginary part, the scattering rate, if you want, is very, very large near the antinode. So that's what kills the quasi-particles. This is the theory. And I think this was the first diagrammatic Monte Carlo paper in which the pseudogap was nailed down in strong coupling. The important message, and I'm gonna skip about a bunch of things. The important message is that there are two messages. The first message is that the mechanism behind creating this pseudogap can be investigated in these methods, both in cluster extensions of DMFT and in diagrammatic Monte Carlo, using this nice fluctuation diagnostics method, which analyzes the contribution of self-energy in the various channels. And it was shown in this very nice paper in DCA that the mechanism is associated with pi-pi magnetic correlation. So this is completely consistent with the qualitative physics of the METS I showed you, which of course came later, that I showed you before. And we reached exactly the same conclusion in that paper using diagrammatic Monte Carlo. Okay? So the physics of the pseudogap opening is associated with pi-pi centered spin correlations. It kicks on at pretty high temperature, right? And it is not associated with a large correlation length at strong coupling. In contrast to the Wilk-Tremblay criterion, you can get a pseudogap even when the correlation length is a few lattices. Okay, so that's the important conclusion for the strong coupling pseudogap. And just to finish, and there's been a lot of work. Actually, these are papers which by Kishen and Manuel, where many physical quantities were compared to experiments in relation to the pseudogap. So I want to end the talk by telling you about the most recent work that we did with Fedor Simkovich, Ricardo, and Michel Ferrero, where we tried to put these things together using now the modern version of diagrammatic Monte Carlo, indeed the CDET algorithm. And what we did in this paper is the following. So in the plane U versus doping, this is T prime equals 0, but we have some ratios for finite T prime. We map out using various criteria that I don't want to discuss right now, but I can answer questions, the region where the zero gap is. So this is the red region. And you see, we measured the magnetic correlation length at the same time. So here there is a zero gap, but the magnetic correlation length is only 2. Okay, so that connects to the point I was making before. And then what these people did is actually they followed this red boundary as temperature is lower. And because this is diagrammatic Monte Carlo, at this point, one can only go down to temperature overhopping of order 0.07. I think that's more or less the maximum one can do. But still, one can do this extrapolation. And this is done here. So this is in units of hopping, quarter of hopping, 1/5 of hopping, and so on, 1/10 of hopping. And you see this zero gap region which invades more and more. And if you are brave enough, you can decide, so this is the best temperature we can do. And if you are brave enough, you can extrapolate this red line, right? Which we did here. So if you extrapolate these red lines for the different temperature, you find this extrapolated red line here. And you see that this extrapolated red line happens to coincide to good precision, at least when we can nail it down, with the black line of Sheway, Zhang, and co-workers that separate stripes and no stripes. So this is not saying that the zero gap is created by stripe fluctuations, because I showed you that there is nothing in the charge physics in this higher temperature region. It's created by magnetic correlations. But this is telling you that at least for T prime equals 0, but we think it's fairly generate, the zero gap state is intrinsically unstable at low temperature to stripe formation. And so that connects the end of what we have seen for many years with cluster embedding methods, and what has been seen also for many years with, say, MPS, Stanson network. Okay, well, this is essentially the end of the story. This is sort of a global picture, if you want. At high temperature, everything is a soup. There is a temperature T star at which there is an onset of pi spin correlations, and that opens the pseudo gap, even when the correlation length in this regime is not that large. Eventually, there is a charge ordering phase transition, the nature of which is not very well understood at this point, but we know it exists. And eventually, there is a stripe ordering or superconductivity, if superconductivity. Okay, that's it.
Short question.
Are we done in the sense of, are the big unknown questions for the Howard model solved to the extent that it's just chemistry is much more important than we should worry about it anymore? Or
that's what you would like to be.
well, this is what I have been saying a couple of years ago. That's why I've sort of left, right?
Yeah.
But what's remaining? Sort of where are the big uncertainties that are still there?
Well, so in my opinion, I would also claim that most of the important qualitative physics of the 2D Hubbard model are now more or less, if not fully nailed down, at least understood. Well, at least revealed, okay? And I would go as far as saying that it's clear now from all the numerics and from all we know that it has all the right ingredients to capture the physics of 5D. Okay. So now, are we done? Depends a bit on what you really want to know. Okay. So if you really want to know, to have clear evidence that the superconductivity is associated with the super exchange, okay, there is a bit more work that needs to be done to document that precisely. If you want to know what is the nature, if you're a StatMech person, like I'm partly, and want to know the nature of the finite temperature stripe phase transition, we are not done. If you want to know how charge modulations and superconductivity coexist at U equal 8 and doping 0.25. There's no data on that. Okay, so now you make your point. But at least at a general qualitative level, I think we are there.
So if I build you $1 billion quantum computer, you can compute the Hubbard model.
Yeah, I'm not going to take it because I don't believe this is going to work. I will use it. Give me the billion. I do something better with it.
A quick announcement, so the next talk is canceled, so.
Oh, I think you were going to announce something about the $1 billion.
Yeah. So we get plenty of time for questions.
Great.
Go ahead.
Yeah, so, thank you for the nice talk. I wanted to ask you about the pseudogap case again. So, you mentioned that it's not strictly related to the stripe order, so meaning that stripe order doesn't imply pseudogap, but could you elaborate more?
Well, you know, I mean, there were some, in the field of the Hubbard model and ITC, all ideas have been put forward, right? So one strand of ideas was that what creates a pseudogap are dynamical stripe coalitions, that there is charge coalition, okay, there is no long-range charge order, but there are, you know, fluctuating stripes, and that's what creates the pseudogap. We don't see any of that. I mean, what we see by any standards is that above, when the pseudogap starts forming, the charge responses, there is no charge response, it's very low. So I think it's really spin physics that creates the pseudogap.
And the second question, if I can, sorry. What is the fate of the pseudogap when you have this T prime, when you consider it is?
It's still there.
It's still
Yeah.
there, so it doesn't, okay.
No,
so-
no, the pseudogap is there in the presence of T prime. I mean, what T prime will do is that it will change the precise location where coalitions shift from pi to Q.
I have the,
Cancel,
I
no,
have,
ask two questions for me.
Victor,
So which one?
Alexei,
Which one?
which board?
Sorry.
Go ahead, yeah.
somebody has to stop.
Well, so the first question would be, so you mentioned several times Berman-Wagner theory, which is very weak with rhythmic diversions of infrared coefficients, which are very low distance.
Correct.
As far as I understand, what you're doing is kind of local. So how can it possibly capture bigger Berman-Wagner?
No, why are you saying what we are doing is local?
I mean, so where is the long distance physics in your calculation?
Well, let me show you. So, well, first of all, what I showed is not all my calculations, it's many different methods, right? So some are using a local approximation, like, but some are not, right? But even cluster extensions of DMFT can be made consistent with Mermin-Wagner and capture the exponential increase of psi. Let me show you a plot. So thank you for the question, because this is something I didn't show. Fine. But when I said that the weak coupling mechanism for the pseudogap is understood, and in the weak coupling regime, psi for example, at zero doping will diverge exponentially. Okay. So, you know, this is a plot. This is psi versus 1/t in a log lean plot, right? And this is a paper we published with Thomas Scheffer that compares basically every single method under the sun. Several of these methods are cluster extensions of DMFT, so-called D gamma A. We can decide how this is done, right? This is completely able to capture long distance physics and is made consistent with Mermin-Wagner. So you see the exponential increase of the coalition length.
But it's consistent because you want it to be true, or it can rediscover Mermin-Wagner for its own.
Okay, so in D gamma A, Mermin-Wagner is actually imposed using the so-called Moria term. So it's admittedly somewhat put by hand. In the diagrammatic Monte Carlo CDET method, it's there by construction, and you also see this large coalition.
Yeah, and I'm sorry. Second question I have, so pseudogap, as far as I understood, it has nothing to do with superconductivity.
Well, I'm not sure about nothing to do in the sense that the spin correlations are responsible for opening the pseudo gap, and we strongly suspect, I mean, there are just undemocratic evidence for this, but that it is also the super exchange that drives the superconductivity. So they are both related to spin physics, but you don't need the pseudo gap to have a superconductor.
But then why difference? Why there is 1,000 people? So
That's a very, very good question. So I think I partly know the answer to it. Cuprates are a very, very rare example. If I take all transition metal oxides, okay, cuprates are among very, very few in which there is a single band at the Fermi level. All the other ones have multi-band, multi-orbitals, right? And it's not the only example. There is another set of material that has single band. Two that I know, two other sets. One is the iridates, also single band for other reasons, due to spin orbit. And the third is two-dimensional organic conductors. All three display the pseudo gap. 2 dimensions, and single band, which leads to strong super exchange.
Connects sort of, because I believe that if we are on the same page about Merlin Wagner, but we kind of different. What important for Anton is that the correlation of length divergent, but there is no phase transition, right? The only important thing is that the correlation divergent.
Well, the only phase transition at finite temperature is in the charge.
That's what I'm trying to say. So,
Yeah.
It's just correlation length, but there is no order which would, there is a spin order which would appear with a stripe
At finite temperature.
at finite temperature. It's minimalistic requirement. It's not like you are interested in something. It's really long range.
Yeah. Anton, I noticed that when you make your criteria for super gap, you use something like imaginary part of sigma with Matsubara frequency.
Well, we also use,
Is it-
yeah, so let me give you a better criterion, which also you can also use on Matsubara axis, okay? So can I use the board? So let me think first about real frequency, and let me think about the spectral function, the single particle spectral function as function of temperature, right? So let me plot this quantity as a function of T. If you're in a metallic state, this quantity will grow as a function of T and eventually saturates metal at finite densities. If you are in the pseudo gap region, what we have,
Depends on momentum.
yeah, at a fixed moment. Let's say on the Fermi surface or somewhere. Yeah. If you're in the pseudo gap region, what happens is that this thing goes down. You lose density of state as you cool. Okay? So this is a very nice criterion. We see that all the time in cluster diversity calculation. Now, how can we estimate this if we don't have real frequency? So if you are at low enough T, what you can do is you can just do in G of I omega n and E. Right? And if you are at low enough temperature, you have enough omega n to extrapolate this to 0 Matsubara frequency. Or if you are cheap, you can even just look at in G of I omega naught, the first frequency, and you will see it. Another way to do that is using the fact that at low enough T, you can.
Is it model dependent?
No, it's not model dependent. The last thing I want to say, the proxy for this, also in imaginary time, is beta G of tau equal beta O. And all these quantities display this behavior. So there is a lot of physics that you can read out from Matsubara frequencies. Not all, unfortunately.
If we have more questions. Oh, on hand.
maybe to follow up on the previous question, so what are now the challenging open questions, perhaps related to generalizations such as including dynamics, disk order?
Well, dynamics, of course, well, dynamics is really widely open. There is no way by which the current algorithms are able to do anything comparable to what can be done in equilibrium. Well, you know that you're working in the field, right? I mean, so dynamics is wide open. There's lots of things to do. Well, you know, there's, again, it depends which level of refinement you want, refined questions you want answers to. For example, as you know, there are some experiments that claim that at this time on the pseudogap line, there is possibly an accompanying phase transition, these loop current things. For cuprate aficionados, there are certainly many questions of that type that are still not answered. A prominent question, okay, maybe a big question, maybe that answers both of your questions. A big question that is not answered, and I didn't touch upon, is whether in any regime, the pure two-dimensional Hubbard model without disorder, compare Avishkar-Stokes, has a strange metal regime of transport. I don't think numerics has answered that question in any convincing way. So if there is one prominent qualitative open question, it's this one. And the connection to cuprate is, do we need to invoke disorder on the coupling constants to account for the strange metal phase? That's probably the last big open question.
Yeah, I just want to follow up on this, two questions. One is this like an empirical observation, or does you expect this suppression density state in the
Well, that's almost a definition of what we call the pseudogap, right? I mean,
no, in the real frequency, in zero frequency, but
yeah,
in Matsubara, it's
no, but you can show this guy as omega. Imagine I know this on the complex imaginary frequency axis, right? But not restricted to Matsubara, right? So obviously, this is just mathematics. As omega goes to zero, this goes to twice times this, right? So the only thing I'm saying is that if you have enough,
or you look at a particular point, you say.
Yeah, you have omega n, and you see a function that does this. So you know eventually.
Yeah. Okay. And the other question is, so
perhaps just the caveat here is, of course, there's always the possibility that some completely different physics happen when omega is smaller than t.
Exactly.
And this is very important for transport. But for single particle density of states.
And the other question is, so there's an angular dependence as you go up on the Fermi surface.
Yes.
This suppression doesn't happen in a node.
Absolutely. That's completely correct. So this is exactly how we detect the pseudogap. So this is your nominal, say, non-refracting Fermi surface. You measure here, you see this.
I see.
You measure here, you see that.
Okay, good.
Yeah.
Have more questions? Not, let us thank Antoine and all the speakers.
Oh, yeah. The refreshments are rigid. No, I was told that there's nothing new. So.
Oh, it's the old.
Okay, anyway,
Okay, we're gonna get started. So we'll be chairing this session. So we're gonna start at 1 and end in 30 minutes. So Massimo, can you hear me okay?
Yes, I can hear you. Am I audible?
I think so. Can you guys hear him in the back there? Okay, great. So Massimo's going to talk about superfluidity of quasi 2D helium droplets on graphite.
All right. Thank you very much. Thank you for the invitation. And today I'm going to talk about some fairly recent work that has been done at University of Alberta by Kirill Kolevsky, who is a master student who's been working with me. And we have been exploring superfluid behavior of droplets of helium-4 on graphite. And I'm going to try and explain to you why this is interesting to us. First of all, we're talking about finite systems, okay? So few body systems, and helium-4 clusters have a fairly old history in terms of subject of investigation. They're very fascinating and highly quantile few body systems. And the initial idea was that one would investigate the possible superfluidity, which is regarded initially as a bulk effect in confinement, in the presence of a surface in a finite system. And in particular, one would be looking at the interplay of what is essentially bulk and surface physics. Now, the first calculation was carried out in 1989, so, some 35 years ago, by Senzang, Sepperli, and Klein. And the main result is summarized in this plot here on the right. Open circles are results for 64 helium-4 atoms, so a cluster of 64 atoms. The filled circles instead represent clusters of 128 atoms. We are looking at the normal fraction, so 1 minus the superfluid fraction. And the dotted line, the solid line instead is the bulk result. So as you can see, there are quantitative differences, but even if you take into account the scale on the left, the result of the surface is relatively small. The effect of the surface seems relatively small, and that is the main conclusion of that article, that the surface doesn't seem to affect significantly the properties, the superfluid properties of helium-4. Now, experimentally, there are a well-established way of generating clusters of helium. You have like a jet, you have a nozzle, and you can do mass spectrometry and determine the number of atoms on each cluster. And it's a field that is now fairly mature. And indeed, over the past 20 years, helium droplets have become an object of great interest, especially because they are the closest thing you can have to vacuum. What you can do is embed impurities, like it's shown here. Unfortunately, I don't see how to get my pointer. Right, laser pointer. Okay, there we go. So the idea is that you have you can put a molecule you're interested in doing spectroscopy on inside a helium droplet below a certain temperature, which is typically a fraction of a Kelvin, like 0.2. The droplet turns superfluid, and this is indicated by the fact that rotational spectra become incredibly sharp. And so this is one of the most accurate ways to do spectroscopy, fundamentally. The notion is that the rotation becomes so unimpeded because the droplet itself turns superfluid. And so the molecule de facto rotates in vacuum. And there's an entire industry at this point, which is now fairly mature, okay? Now, the question is, would it be interesting to try and go 2D, okay? Now, there are very good reasons for trying to study systems in reduced dimension, and I don't have to expound on them to this audience. But let me just remind you that, by reducing dimensionality, one enhances quantum mechanical effects. How does one go from 3 to 2D in practice? Well, there is a new field that is called atoms, and there you can use external fields, and that's a completely different ball game. That's fair. I'm not going to discuss that. Otherwise, traditionally, the way you can find motion of atoms and molecules to 2 dimensions is by absorbing on a substrate. The substrate itself can be seen as an element of complication, but also a way to give rise to a richer physics, which in a 3 dimension you don't have access to, because you have the corrugation of the substrate, which imposes its own physics to some extent to the adsorbate. And so one can use this as a playground to investigate the interplay, if you like, between superfluidity and localization. And more recently, this seems to be a good setting to investigate more exotic scenarios like that of transverse quantum fluids we heard about yesterday, for example. And the idea is that to look at what happens on the perimeter of the cluster, whether one has quasi one-dimensional behavior of something more complex than that. All right, so what do we know about helium-4 clusters in 2 dimensions? Turns out very little. The same quantum Monte Carlo methodology that was so heavily utilized to investigate clusters in 3 dimensions has not really gone very far in terms of giving comparable results for clusters in 2 dimensions. And the reason is that in 2 dimensions, these clusters are considerably less bound. And so already at the typical temperatures at which most of those simulations are carried out, which is 1 Kelvin, they evaporate. But I would like to make clear here that I don't mean to evaporate. By evaporation, I don't mean to get detached from the substrate. That's, of course, it's a problem in and of itself. But at 1 Kelvin, that's not so much the issue. The issue is evaporation on the plane. In other words, they don't stay together. One way in which traditionally people have tried to overcome this problem is by imposing an artificial, of course, unphysical confining potential, which will keep things together, but then you have to extrapolate one way or another the results to the limit in which the potential is rendered weaker and weaker. And as you certainly understand, this is a far from trivial procedure. Now, this is particularly the case for helium clusters. If you go to slightly more bound clusters like perohydrogen, this is really not a problem because they stay together. And the reason is that perohydrogen is solid in the ground state, even in 2 dimensions. And clusters are solid-like already with as few as 6 or 7 molecules, okay? They form geometrical structures already in purely 2D, in other words, without a substrate. And there have been a number of studies already of these. It turns out if you have fewer than 20 molecules, you see something that resembles a supersolid in the sense that you have concurrently localization of molecules and exchange, superfluidity related to exchange. Now let's talk about what one could do in terms of stabilizing real quasi-2D clusters, which presumably could be studied with fairly advanced techniques like STM. There are 2 things that can happen with a substrate. This is what you would expect if you have a very strongly attractive substrate like graphite, for example, in which a helium droplet will try to spread out as much as possible. So I don't know if I have been able to reproduce the scale correctly. I have here 64 helium-4 atoms at a temperature of 0.1 Kelvin. And as you can see, they spread out, and the thickness of this film is what? 1 angstrom, all right? And look at the scale. This is I call it X, but it should really be R. It's the radial scale. Okay. Now, as you can see, the film itself sits at about 3 angstrom from the substrate, and of course, at this distance, a graphite which is so highly corrugated will impose its own pitch on the droplet itself. So helium-4 atoms will end up being pinned, and you will observe crystallization, essentially, of the cluster on the surface, which is obvious. I remind you that there is no other way of having a cluster of helium which is solid-like, because helium at equilibrium is a fluid. If the substrate becomes less and less attractive, so increasingly weak, 2 things can happen. Number 1, take the case of, for example, of alkali substrates, which are typically fairly weak. What can happen is, first of all, as you can see, the droplet itself sits further away from the substrate, which means its corrugation is less important. But then what you have is the helium atoms like less and less the substrate and more themselves. And so the droplets start beating up, okay? This is a typical phenomenon of non-wetting, which occurs, for example, on cesium or rubidium. And it's interesting in and of itself, but we're not talking really what we have in mind when we say 2D clusters. we would like to be more in a situation like this one. So there's a bit of a competition between trying to spread things out, but keeping them together and having to take into account the corrugation, or using weak substrates in which you have this potential effect. So here we focus on the limit in which we have the strongest, most attractive substrate, which is graphite. And of course, we have to take into account its corrugation. Now, helium on graphite has been studied for half a century, more than that. Both experimentally and theoretically. One thing that we know is if you take the first ad layer, then there are only crystal phases. You don't have a superfluid monolayer on graphite. In particular, there are two crystal phases, one which is commensurate with the substrate. You have to imagine here that the solid dots, the black dots are the carbon atoms, and these are the helium atoms. And the density is given by this number. This phase is referred to as C1/3. There are other commensurate phases separated by domain walls as you increase the coverage, the density of helium atoms adsorbed on the substrate. Eventually, you move to a regime in which you have an incommensurate crystal. In other words, you have a high pressure 2D helium, but that's bulk at this point, and it forms its own incommensurate triangular crystal. And eventually, at this particular coverage, you start having second layer promotion. Now, we are interested in investigating this regime, in other words, below commensurate density, to where you start forming clusters, okay? And we know that if the coverage is fairly large, below equilibrium coverage, but still fairly large, you have large helium clusters on graphite. But the question is, what happens when these clusters become nanoscale? In other words, they comprise 10, 20, 50 atoms. So we are interested in doing the most accurate possible study of nanoscale size clusters on graphite. And so we have an interplay of corrugation and superfluidity. So how does a crystalline order emerge as the size of the cluster is increased? And do we have any superfluidity for sufficiently small clusters? And how does the system behave along the perimeter, the surface of the cluster? These are the questions that I would like to address today. How do we do the calculation? So we use quantum Monte Carlo simulations and at finite temperature, basically the continuous spaceworm algorithm. I don't think I need to give the details to this audience. The idea is that we have a system which is a methodology which is fundamentally numerically exact, at least for both systems, and we can handle essentially arbitrarily complicated interactions. So we start out with a many-body Hamiltonian, which includes the kinetic energy of all the helium atoms, which are elementary particles. We have the Aziz per potential describing the interaction between two helium atoms. So this is a fairly well-established potential. Equally reasonably well-established is the Carlos-Coll potential describing the interaction between helium atoms and the graphite substrate. The idea is that we want to account microscopically for the effect of corrugation. This particular potential has been studied in just about all similar studies of helium and graphite carried out in the past. Its accuracy, in my opinion, is unknown. It is obtained by superimposing the effect of many pair helium-carbon potential, and you can sum the contribution of all the carbon atoms to a large extent analytically, depending on the particular form that you pick of the interaction. And then you try to reproduce some non-experimental data, but there are ambiguities in doing that. And so this is the best we can do so far. We expect that it should capture at least qualitatively and even semi-quantitatively the most important aspects. We use a simulation cell which is approximately 200 angstrom. Of course, the simulation cell has to be chosen so that it fits a commensurate number of carbon atoms, and we use the primitive approximation for the propagator with this particular time step. What do we calculate? Well, we would like to obtain density maps of helium on graphite. We would like to calculate radial density profile computed with respect to the center of mass of the cluster. And one thing that is important is, of course, the superfluid response of the cluster. We use the two type of estimators. One gives the global superfluid response, which is the area estimator introduced by Senzeng, Seppelin and Klein in the same paper in which the calculation for a 3D clusters was carried out. And also we would like to see what the local superfluid response is. And for that we use an estimator introduced by Kwon et al. Considerably later. It is still based on the area estimator, but it decomposes the contribution in terms that can be attributed to specific spatial positions. So let's look at the results. So basically, this summarizes the kind of results that we obtain. So let's spend some time discussing these. First of all, what is it that I'm plotting here? The small dots are the carbon atoms. So you're taking a top view of the graphite substrate, and these are the traces of all the atoms. All right. They are quantum mechanical, so they are the single particle paths. Because particles are indistinguishable, in Feynman's formulation of statistical mechanics, paths can become entangled. And it's precisely this kind of entanglement, quantum exchanges, that give rise to superfluid response. So let's begin with a cluster that has as few as 16 particles. So the results that I'm going to present are all at temperature of 1/8 of a Kelvin. We have observed that as long as we're willing to do the calculation at temperatures below approximately 0.15 Kelvin, these clusters stay together as long as we have at least 7 atoms, which is a fairly small cluster, okay? So this represents, for all of these clusters, the typical density profile in the direction perpendicular to the substrate. So as you can see, the cluster is sitting at approximately 3 angstroms away, which is expected, and half width at half maximum is what? Probably half an angstrom or something like that. So this, in real terms, is as 2D as you can get. Okay, I mean it's very hard to go even more 2D than this. Graphite is arguably the strongest attractive substrate that you have. There will still be, of course, some zero-point motion in the perpendicular direction. With that being given, however, when you have only 16 atoms, as you can see, all of the traces of all the atoms are entangled, and you can already tell that the underlying substrate doesn't really make much of a difference. Okay. This cluster at 1/8 of a Kelvin is 100% superfluid. And as we shall see later on, there isn't really much of a difference between this cluster and the cluster that you would have if it stayed together on a flat substrate with the same overall strength of graphite. We have done some numerical experiments of this kind, and I will discuss them more in detail later. As soon as you start increasing the number of atoms, you see clearly what happens. You start germinating the C1/3 commensurate crystal phase. You see that all of these atoms go and occupy the preferred adsorption sites on the graphite substrate. And this nucleates from the center and slowly expands toward the surface. However, what is interesting and remarkable is the fact that you continue to have entanglement of world lines on the surface, and it persists all the way up to 64, even though, of course, it becomes less and less important in terms of the global system, but it remains. Nevertheless, the superfluid response is seen to decrease fairly rapidly with system size, and we will come back to this point. So let's fix the temperature at 1/8 of a Kelvin, and we're going to describe now the radial density profile and the radial superfluid density profile. In other words, we're looking at where it is that the system is superfluid. So let's begin with 16 atoms, and here I'm plotting both the radial density, which is the solid red line, and on the right, I have the local superfluid density, which I'm representing by these spikes. So this cluster, and it's radial, okay? So this cluster is approximately 100% superfluid. And as you can see, well, okay, except maybe this area here, nevertheless, it's on the surface and right in the middle, it is essentially entirely superfluid. The density profile is very smooth, featureless, and it is basically, again, the same thing that you would have if you were to do this study on a smooth substrate with the same overall average attraction as graphite. As we start going to 24, you see that this starts acquiring structure. And I remind you that with 24, we already have the formation of a central crystal cluster. As a result, the superfluid response begins to be pushed toward the surface where exchanges continue to occur, whereas they become suppressed in the middle. The dotted line is the density profile of a cluster with 24 atoms on a smooth graphite substrate. Again, this is defined as a hypothetical substrate that has the overall same attractive strength, but is smooth, doesn't have any corrugation. As you can see, in that case, we would have a cluster that would stay together. The value at the origin is very close to the 2D equilibrium density of helium-4, which is 0.0432, and it would be 100% superfluid. On the other hand, if we take into account the corrugation, then the superfluid response is depressed to approximately 50%. And the same trend goes on if you increase to 32 first and 64. You see you have these peaks, all right, very well defined, all right, which are consistent with the formation of this crystal core in the middle, while exchanges are confined to the surface. Now, as you can see, on the surface, there's this response that seems resilient. On the other hand, the overall signal rapidly gets suppressed. So we have about 10% at this temperature with 32 atoms, and by the time we get to 64, we have 2%. We have results for 128 atoms. There are exchanges involving up to 7 or 8 atoms right on the perimeter, but there is no measurable superfluid response. So altogether, this seems consistent with the notion that for this particular realization of a 2D system, the perimeter behaves more like a Lottinger liquid rather than a transverse quantum fluid. We do not observe the phenomenon of superclining that characterizes instead a transverse quantum fluid. So what is exactly the basic physics at play here? So the idea is the following. On the surface, on the perimeter, atoms are fairly loosely bound and they can move relatively freely, although of course there is still the underlying substrate which is corrugated. Nevertheless, it is always possible for these atoms to exchange. Now, in the bulk, we know that in order for paths that involve exchange of identical atoms to occur, the other atoms have to move out of the way, okay? Because the interatomic potential between two helium atoms has a hard core. In order for the action not to blow up, you have atoms to move out of the way. Now, it was first, one of the brilliant intuition of Richard Feynman was that if you have a translational invariant, essentially hard sphere like Bose system like helium-4, you can have these exchange paths because the idea is that the action will not be increased dramatically if you include the contribution to the kinetic energy attributed to atoms moving out of the way, okay? So what you need is a relatively small number of atomic displacements to avoid overlap, but with that you can have paths that involve exchanges that are competitive in action, okay? And therefore, that's how you end up with the superfluid. But that, of course, assumes translational invariance. If you have a strongly corrugated substrate in which there exists preferential adsorption sites, in other words, potential energy minima that atoms want to sit at, even small displacement can be energetically costly because of the change in potential energy, which if the substrate is smooth, isn't there. And so if more and more atoms are involved, then the action associated to large exchange paths is going to be such that these will not occur. So if you keep the size of the cluster relatively small, then these paths continue to occur because they involve relatively few particles, but it doesn't scale well with the number of particles, and therefore, as you increase the size of the system, you're going to have essentially dead matter in the middle, a crystalline cluster, like in the case of 64, and only exchanges confined to the surface. So this is, of course, the limiting case, because it is well known that graphite is the most strongly attractive substrate. The idea is, can one engineer another substrate which has significant corrugation, where clusters this small are going to be still stable, but where exchanges are going to be possible, and therefore you're going to have something like super solidity, quote unquote, of course, because we're not talking bulk. Well, that's the question. We have tried graphene, which is just one layer, fundamentally, what would be graphite. Otherwise, the physics appears essentially the same, because the overall reduction on the strength of the potential is approximately 10%, but there are nevertheless many other substrates that one can consider, and this is certainly what we're working on right now. So let me summarize. This seems to be a very interesting system, okay? Because it is possible with this to study the interplay of superfluidity and localization in a way that is more direct than what you can do in 3D, okay? The fact that you are in 2D and you have so much technology to observe, to do in situ observation of what's going on, appears to be an appealing prospect for gaining understanding. Now, we increase the size of the cluster, the physics evolves from essentially entirely superfluid, if you have a very small cluster. So a sufficiently small cluster is fundamentally the same as a free 2D cluster. This behavior is qualitatively different from that of 2D perohydrogen clusters, because those are solid on their own. They don't need a corrugated substrate. The reduction of the superfluid signal with cluster size appears to suggest that the surface region behaves more like a conventional Luttinger liquid. Okay, again, possibly on a weaker, still corrugated substrate, things could be different, and more interesting scenarios could be accessible. So let me conclude by, first of all, thanking the person who did all the work, and I'll be happy to take questions.
Okay, Massimo, thank you for the nice talk. Can you hear me okay?
Yeah.
Okay, good. So we have a few questions. Let me go ahead. Sorry.
But where am I supposed to speak to?
I think you can talk now.
Massimo, do you hear me?
Yeah. Hi, Boris.
So, hi, Massimo. How are you? So you told us that you do not see superplane phenomena, and that's why it's up in a liquid rather than transverse quantum fluid. You do not see it because you didn't look at it. Like, if you don't see the point, you don't see it, or what? So, because to see superplane behavior, you need to study fluctuations of the shape. You cannot just look, make a snapshot and say, "Oh, here we go." That's you really need to study correlations, blah blah blah, imaginary time and stuff. So the protocol which you can see in our work with Nicola and collaborators.
Okay, correct. But I thought that in the case of the transverse quantum fluid, you would not have. So does it not? The superfluid response. How does it scale with the size of the system?
It scales like long-range order at zero temperature. It's just finite superfluid stiffness.
That's right. So
you cannot.
Temperature is not final.
Yeah.
It's fine.
It does matter. So a superfluid response in transverse quantum fluid is not particularly different from the superfluid response of a Lagrange liquid. It's only if you do finite currents, you can see the difference in terms of instantons. But in terms of basic superfluid stiffness, the two behave absolutely similar.
Okay.
Superfluid response cannot tell you the difference between one and another.
Oh, okay. Okay. No, I was under the impression that I could do it just by
It
looking
was
at
a
the.
wrong impression.
Okay.
Next question.
It's actually along the same line. By looking on your pictures, snapshots of the clusters, you can see that the boundary is rough. So this might be a signature that this is actually effective supermodel.
Right.
So
Yeah, but the
I don't
boundary is
agree
always
also
going to be
with your
rough.
claim that this is Latinger liquid, clear-cut Latinger liquid, just the opposite.
Okay, the
It's
boundary is
the
always going to
clear-
look rough one way or another, but I agree. So, yeah, one would have to look at the correlation. Of course, it becomes difficult because we still have a fairly small system. So we would have to increase the size of the system significantly to where we have a decent amount of statistics. My impression is that if you look at a system like that, the boundary will always look rough because the particles on the boundary, on the perimeter, are always going to be loosely bound.
That's a separate point, but you, to make a claim that it's a Lagrange liquid rather than transverse quantum fluid, you need to show something beyond the superfluid response. You really need to study quantum fluctuations of the shape.
Boris, I simply said that it seems consistent. I didn't say that it is a Latinger liquid.
Whatever is superfluid is consistent with Lagrange liquid as long as it's one dimensional.
Yeah.
Any other questions? Okay, let's thank Massimo again.
Thank you.
Oh, yeah. So, you need a pointer. Oh, there. Great. Our next speaker, sir, he's coming from UMass Amherst. He's going to tell us about chiral states in XXC chain. Thanks.
Thank you. My thanks to the organizers, team, Macaulay, for serving me. Thanks to the chair for not kicking me out after 40 minutes. So, yeah, so today I'm going to talk about chirality in XXZ chain, and the motivation for studying chiral properties of this one-dimensional chain is precisely coming from two dimensions, as Leonid Levetov discussed in his talk yesterday. But because this is going to be a one-dimensional talk, so I will mostly emphasize one-dimensional properties and also, which is also partly integrability of properties of the chain. Okay, so here is the reference. The work is done in collaboration with my student Shannon Wei, who is moving to University of Alberta for scholarship, and my former short-term postdoc Bagash, who is in Germany. Okay, so one-dimensional Heisenberg model, sure everybody is familiar with. So this is one-dimensional chain of half spins. The Hamiltonian is given by the spin exchange interaction, Ising interaction, and in the presence of an external magnetic field, there is the Zeeman term, HSZ. So it describes certain class of quantum magnets in one dimension. At the same time, the model can be rewritten with the help of spin rising and lowering operators, which can be mapped onto hardcore bosons. And therefore, the model is also a model of hardcore bosons with some where the magnetic field term now becomes a chemical potential term for these bosons. And the model has been realized in multiple atoms experimentally. And finally, the same model can be mapped onto spinless fermions with the help of Jordan-Wigner transformation. So it describes spinless fermions with kinetic term, density-density interactions, and again, magnetic field transforms into a chemical potential for fermions. Okay, so this model is well known, it's well studied by many methods, including exact solvability, the beta-ansatz method, coordinate beta-ansatz method, and algebraic beta-ansatz method. So the phase diagram, the entire phase diagram in the presence of the external magnetic field and anisotropy delta is here. So if we measure these two energies in the units of J, so this becomes a two-dimensional phase diagram. I will describe it in a moment. Also, the model has a gapless phase, which can be studied by bosonization techniques. And here is perhaps an incomplete list of quantum materials that are described by this model. Okay, so the model contains gapless. So in the absence of an external magnetic field, the phase diagram is one-dimensional. Basically, the space is defined by the anisotropy parameter delta, which is this interaction here. So when delta over J, delta divided by J, when it's between -1 and 1, the phase is gapless. It's an XY paramagnet with power law correlations. Described by the Tomonaga-Latinger liquid field theory. When delta is greater than 1, we have Ising antiferromagnetic order with gapped spectrum, and when delta is smaller than -1, we have Ising ferromagnetic order with gapped spectrum. And this point, delta equal to 1, is a special point. This is X Heisenberg chain, which has this SU2 non-abelian symmetry. So I will mostly be concentrating on this limit throughout my talk, and just at the end of the talk, I will briefly show the results for arbitrary delta. Okay, so the spectrum, as I mentioned, is of Heisenberg model is when delta is between -1 and 1 gapless. In the Heisenberg point, the correlation functions decay as a power law 1 over distance with some square logarithmic prefactor in front of it, while in the XY paramagnet phase, correlators decay as a power law with powers determined by the Latinger parameter, given by this formula here. Okay, so this is all well known, well established, and this is the phase diagram in the presence of an external magnetic field HZ. HSZ. So this is the magnetic field. This is anisotropy parameter delta. So this XY paramagnetic line between -1 and 1 becomes now this region here, which is still XY paramagnetic region. The whole region is gapless. The spectrum is gapless. However, and this is something I'd like to emphasize here, which is well known, of course, at the end, in the presence of arbitrary weak external magnetic fields, the system acquires finite magnetization. Magnetization is proportional to the magnetic field. Okay, so along this line, magnetization is 0, but once we introduce even infinitesimally weak magnetic field, the system acquires finite magnetization. And we have this ferromagnetic phase to the left and antiferromagnetic phase to the right with our gapped phases. Okay, so this model is integrable even in the presence of an external magnetic field. The simple reason is that this Zeeman term commutes with this XXZ part of the Hamiltonian. The commutator is 0, And this is, which means that this is the Zeeman term is basically conserved quantity in the Heisenberg model. Conserved quantity, we say it's the first conserved quantity, not because of this historical reason, but because of this is Q1, means that it is a sum of operators defined on a single site. Okay, it's a sum of SC operators, each defined on a single site. That gives us the first conserved quantity of the model, which is a Noether current corresponding to the U1 symmetry of the Hamiltonian. Okay, so it is conserved. So this portion can be diagonalized simultaneously with this portion, giving rise to this nice phase diagram. Exactly. All right. So in my talk, I'm going to ask another question. Before I ask my question, let us try to understand what are the other conserved quantities of the Hamiltonian. So beta ansatz gives us the machinery to basically generate all quantities of the model. So we have a finite size system, let's say with sites n, then the system contains n conserved quantities. When n goes to the infinity in the thermodynamic limit, we have infinite number of conserved quantities. And one possibility of generating this operator, all these conserved quantities, is based on the so-called boost operator method. So the boost operator is an operator which is a spin exchange constant J times sum of Hamiltonian densities times number corresponding to the site number J here. Okay, J times Hamiltonian density defined on J and J plus 1. This is some operator. I don't want to talk about the physical meaning of it, which is relevant. It's a sum operator which helps us to construct all possible conserved quantities in the system. For example, if we take this boost operator and commute it with the magnetization, which is a conserved quantity in the model, that will give us the second conserved quantity, Q2. And Q2 is going to be defined on two neighboring sites. Okay? This is going to be a sum of operators, each defined on two neighboring sites. And then subsequently commuting B with Q2 will give us Q3 and so on. So there is this way of constructing all possible conserved quantities based on the previously known one. So as long as we know Q1, as long as we know the boost operator, so we're able to construct all possible conserved quantities. So for example, the second conserved quantity of the model, which we can find by commuting boost operator with this Q1 net magnetization, gives us nothing but the Hamiltonian itself, which is a conserved quantity. And naturally, their linear combination is the Hamiltonian in the presence of an external magnetic field, which can be solved exactly with the help of beta ansatz. So if we go further, yeah, and that gives us this phase diagram, which I briefly discussed. And one important thing is that in the presence of finite magnetic field, system becomes, in this paramagnetic phase, it becomes magnetized, and this magnetization grows up to this critical field, after which the system is fully magnetized and magnetization is equal to 1. Now, the question I would like to ask is, based on the third conserved quantity, Q3 here, which is a sum of operators each defined on 3 neighboring sites. Okay, so this is a scalar, and you can identify this, the third conserved quantity with the chirality operator Leonid Levitov discussed in his talk yesterday. Okay, so this is the third conserved quantity of the Heisenberg model, isotropic Heisenberg model. Here I'm switching to isotropic limit when delta is equal to 1. And then we have all other conserved quantities, which are at the moment of reference. So the question I'd like to ask is the following. What happens if we consider this term in the Hamiltonian? Do we get what do we get for the phase diagram, basically? So this term, we can immediately see that because it's a triple spin product, its total scalar chirality, this operator is a zero for coplanar spins. If the spins are residing in the same plane, operator is just by default is a zero. So basically, it tries to take the spins out of the plane. Unlike antiferromagnetically ordered spins, which are ordered in a plane. Okay. So the question I'm asking here is that, in simple words, can be put as follows: what happens if we replace this net magnetization term, the Zeeman term, by this chirality term? Do we have a similar situation when we, for any arbitrarily weak fields, here we had a magnetized phase? So do we have a chiral phase for any weak alpha here, any non-zero alpha here, or the situation is different? So this was, to me, it seemed to be like a very quick project for my student to master Bethe-Ansatz technique, to add it to his kind of arsenal of techniques. I was thinking maybe, okay, introducing very weak alpha will make the whole ground state to be chiral, and much like it happens in the presence of a magnetic field. So yeah, I basically suggested this to my student, who quickly came back to me saying, no, nothing like that is happening. Actually, ground state, so this is the ground state energy as a function of alpha, as a function of the strength of the chiral interaction. As a function of alpha, remains exactly the ground state of Heisenberg model, up to some critical value, after which the ground state energy becomes a function of alpha. Okay? And if you look at the expectation value of the chirality at the ground state, it remains 0, 0, 0 up to this point here, up to the critical value, and then it becomes finite and starts singularly growing, then becomes a quadratic function. So this was surprising, because this is in drastic contrast with what is happening in the presence of an external magnetic field. While, I mean, from the point of integrability, having chirality here or magnetic field here, we're just adding a conserved quantity to the Hamiltonian, so nothing different should be happening. This was kind of the logic. But in fact, if we, instead of magnetic field, consider chirality in the Hamiltonian, there is a transition from Heisenberg phase to a chiral phase. So the transition, so this is basically the blue line here corresponds to our exact analytical calculations based on Bethe-Ansatz method, while the dots here represent the MRG calculations. Okay, so what we see here is that chirality is 0 up to the critical value, and it becomes growing linearly as a distance from this critical point, linearly in terms of this alpha here. Okay, and one more information that also follows on Bethe-Ansatz, that okay, the situation is different at finite temperatures. Once we introduce a finite temperature T, then chirality starts immediately growing as a function of alpha proportionally to T squared. So chirality basically is alpha times T squared. So at finite temperature, the situation is somewhat similar to what's happening with the magnetic field situation. But at 0 temperature, there is a phase transition at some critical value of alpha. Okay. So what we can say at this moment, so there is, and for this Hamiltonian, there is a critical value of alpha divided by j, which we found that it is equal to 2 over pi. So for values smaller than 2 over pi, we have Heisenberg phase, exactly Heisenberg phase with 0 chirality. For alpha greater than 2 over pi, we have a chiral phase, with the chiral Heisenberg criticality. So the Heisenberg phase is well understood in the thermodynamic limit, when we also consider the continuum limit. The description of the model is a field theory description, which is well understood. This is the Wiener-Witten model. This is a conformal field theory, which has its own very interesting properties. For instance, its central charge and some other characteristics describing the space, giving rise to these right correlation functions. Okay, so all that is well known for the situation when alpha is smaller than 2/5. But now there is a question about understanding what's happening with this when alpha is greater than 2/5, in particular where alpha is much greater than 2/5, when this term can be neglected. So this raises an open question: what is the field theory that corresponding to this chiral Heisenberg phase, and also what are the transition? What is the nature of this transition? So most of the questions that I just pointed to are still open. So I'm going to, in the remainder of my talk, I'm going to tell you what we know.
So, question, so if the low alpha limit, there's no chi, so you're saying that the chiral correlations are not there?
Yes.
Okay, so it's not that it's already there and it's just flat in energy.
Exactly.
It's just coming, it's potentially some excitation coming down.
Exactly. So this is what I'm going to describe now. Yes. So what we could extract from our studies, analytical and numerical, so this is the energy, ground state energy is exactly equal to the Heisenberg ground state energy up to the critical value. Then it starts scaling with alpha. So we try to look at this region and to understand what is going on there with the spectrum. Yes.
Quick question. So since you're changing Hamiltonian just by adding a
Quantum.
yeah, your eigenstate should be the same, right?
The same
It's just that your energy function is changing.
Yes.
Not the beta equations.
Beta equations are the same,
Yeah,
but
just
energy is
energy
different because this is a
So what
third
is
and
the
third
like,
one.
how much is what is the additional term in this energy function? It have its
I have it written down here, it's just derivative. If you want to. These are the beta equations, this is the additional term, which is derivative of this guy.
basically have the competition with J and
Yes.
this term. And as in the Heisenberg case, it's just one string, so it's like just real roots.
Yeah.
What are the roots?
We can discuss this in details later. This carries little physical meaning. All right. So this is what we could extract. What's happening near this transition point? What happens is that this chiral states. This is alpha. So let's say alpha is 0. This is the spectrum of the Heisenberg mode, which understand well. So some high energy states are chiral here. What happens when we introduce alpha, these states acquire lower and lower energy. And they scale with alpha somehow. And after the critical value, they start getting some level crossings here. And in the limit, in the thermodynamic limit, when n goes to infinity, basically this level crossings become like almost like continuous. So we have kind of like a continuous region of level crossings here. And this is the region where the energy scaled with alpha minus alpha critical here quadratically. At some point, one of the high energy states, like highest chiral energy state, crosses this energy, the previous energy at some point, after which the energy starts scaling linearly with alpha as it does for this high energy state of the chiral.
You're talking of some band of states, right?
Yeah, it's a band of states.
Oh.
So this is the spectrum. When alpha is equal to 0, this is the spectrum, whole spectrum from the lowest energy state up to the highest energy state. Some of these high energy states are chiral.
Yeah, but you're saying that they're kind of are bound from below. So there are two lines which are kind of bound.
So there's like huge number of chiral states. Their energies go down.
A little bit sort of continuum of your system.
Continuum.
This continuum would have an upper and lower bound.
Exactly.
That's what I'm saying.
Yeah. So this is
that's what I
this
mean
is
by
J.
talking of the band.
Okay, so as I mentioned, these results were obtained analytically the blue line and numerically the dotted lines. So I should emphasize here that analytical calculations based on the beta answer that gives us this thermodynamic potential, which is the ground state energy when temperature is equal to 0. This formula and this model actually was studied first and solved first by Alex Hitzfeld, who is here, back in 1990. So, and what we did is we basically analyzed this expression closely and found this transition in that expression. And we also kind of continued solving this model, found exact analytical expression for the chirality expectation value that's written here, and found this transition also the level of chirality. So chirality 0 until the critical point, and then it starts scaling with alpha. Okay. All right, so, okay, the back-canvas gives us a lot of information, but the question is how to understand this transition. How can we see it classically, for example, just by assuming large spin and what's happening to this ordering of the spins. Okay. So here's the argument what's happening classically. Let us suppose that the spin is really large. So this term in the Hamiltonian favors antiferromagnetic ordering, when J is positive. And this term of the Hamiltonian favors the chiral order. So what is the chiral order? Chiral order when it can be understood as follows. So this term is minimized when each spin makes an angle pi minus theta with the neighbor. Okay, so the angle between this spin and the neighboring spin is pi minus theta, while the angle between this spin and the next neighboring spin, the third spin, is theta. Okay, so that's the rule. Now, if you think about it for 20 seconds, you will realize that this cannot, no way this can be a planar state, because this was planar, the angle between these two was theta, between these two was theta, then it should be 2 theta between the first one and the third one. But as I said, the angle between this and this should be theta. So then it means that it should go out of the thing. Okay, so that's the angle configuration, and we just can calculate, assuming some small theta, we can calculate how much energy do we gain from this term and how much energy do we lose from this Heisenberg term, and then see the comparison with the energies. So the energy cost for assuming some chirality for this Heisenberg term is scaling with J, quadratically with the spin, because this is S squared, and quadratically with the angle of theta. So this is how much energy we kind of lose from this, assuming chiral order from this term of the Hamiltonian. But the amount of energy we are gaining from the chiral term of the Hamiltonian is also proportional to theta squared. So it's alpha S cubed, because we have triple spin, and theta squared. So we have theta squared here, which means that an alpha here. So which means there is some critical value of alpha for which this chiral order becomes energetically favorable. So there is some critical value classically, of course, because of quantum fluctuations, to some quantum value. Okay, so this is how we can understand this transition just classically. Okay. So what is the phase? What do we know about this chiral Heisenberg phase? About this chiral Heisenberg phase, we know that it is when alpha is very large, away from this transition point or region where we have this low level crossings. When alpha is large, we have that this is a conformal field theory, and by measuring numerically the entanglement entropy, we see that it fits well with the so-called Calabrese-Cardy formula, exact formula for the entanglement entropy in conformal field theories, and that this gives us the central charge of the field theory describing chiral Heisenberg model, and we find that the central charge is equal to 1, much like the central charge is 1 for the Heisenberg portion of the phase vector. Okay. We also did some finite size scaling analysis of the energy. So in conformal field theories, it's known that the finite size correction to the ground state energy are universal. So the 1/n correction to the ground state energy, so the correction to the ground finite size correction to the ground state energy, which is proportional to 1/n, and as the system size, is a universal constant, something like pi squared over 12. So with my student Kerr Wang back in 2020 case at the University of Chicago now, we generalized this result to the presence of the time reversal symmetry breaking. So we show that this universal constant, pi squared over 12, becomes a universal function of the time reversal symmetry breaking field. In this case, this time reversal symmetry breaking field is alpha minus alpha critical times n. Okay, n is the system size. And so this full line is the exact analytical expression. We have this for this scaling function g, the presence of time reversal symmetry breaking. These dots represent our numerical simulations for the chiral Heisenberg case. Of course, there's some room for improvement, but we already see that it fits. The shape fits our universal function. And the central charge, which is a coefficient in front of this universal function, is again equal to 1. Okay, so that also kind of supports the idea that central charge should be 1, corresponding to the chiral Heisenberg phase. So another thing okay, so this is we have seen central charge 1 for Heisenberg model, central charge 1 for the chiral Heisenberg model. What is the difference between these two field theories? So what we could understand, to understand the difference, one has to look into low energy excitations and their symmetry properties. For example, in the Heisenberg model, it is known that the low energy excitations, the domain-wall excitations, are created by the spin operator, sigma x, and the spin operator, sigma x, transforms under parity and time reversal symmetry like that. So it transforms, giving rise to the minus sign in front of it. Okay? So this means that, okay, the Heisenberg model is time reversal and parity symmetric, but this is the rule of transformation. This is how the low energy excitation basically transforms under PT symmetry. Now the question is whether the low energy excitation of the chiral Heisenberg phase has a similar PT transformation or not. To answer that question, we first need to understand what is the operator creating the low energy excitations. So we looked into this problem and found this operator. So it's a gate operator acting on a single side of the Heisenberg chain. So it's again 2x2 matrix, which leaves, let's say, spin down component of the spin residing on side n unchanged, but it gives a phase to spin up component, exponent I5. And this phase knows about the location of the spin we're looking at. It knows about the location and it knows about the system size, capital N. Okay, so this pi here is supposed to be capital pi. It's the parity of this product. Okay, and this is 2 pi number of the side divided by the capital N. And Pn is basically this 2x2 matrix. Okay, so this operator is the one that is creating low energy excitations. So this is what we were able to find. So this operator is responsible for creating the low energy excitations, and we can look how it transforms under time reversal symmetry and parity symmetry. So what happens is that it transforms given that the plus sign here. So basically the symmetry properties a little bit enhanced, improved. Instead of minus sign, there's this 2 plus sign, which means that in the language of this language comes from topological field theories, but in fact, it's called this improvement of the sign called symmetry enriched conformal field theory. So this means that we're dealing with central charge 1 conformal field theories, but which are kind of enriched, which have enriched symmetry. But still, the nature of the conformal field theory is unknown. So this is my last slide. So far I talked about the Heisenberg model when delta is equal to 1 in the presence of this chiral interaction. We saw that there is a transition point when alpha is equal to 2 over pi. And this was possible to obtain because of the integrability property of the model. Now, in the presence of arbitrary delta, the model is no longer integrable. So what we did some VMRG studies of the ground state of this Hamiltonian for arbitrary delta, and found that the phase diagram changes. So the phase diagram has this region, this basically XY paramagnetic phase with zero chirality. So when delta is equal to 1, this dotted line represents Heisenberg phase, XXX phase. As we go to smaller delta, we enter the XY paramagnetic phase. Precisely the same XY paramagnetic phase as we have like for of equal to 0. But then upon increasing alpha, there is a transition, and this transition is of the same nature that the transition is at 2 over pi. So this transition point, I should say that it is not conformally invariant transition. At that point, conformal invariance breaks because the relativistic invariance breaks. It most likely, we believe it's a Lifshitz type transition with dynamical exponent 2. But at this transition point, it looks like the spectrum is quadratic, not linear. So we have this chiral phases at large alpha and very small, like negative alpha. Chiral phases, which are mu. Again, these are gapless phases. These are chiral but gapless phases. So the nature of the theory describing these phases is not yet known. And of course, we have antiferromagnetic and ferromagnetic regions here. So the message is that this region between ferromagnetic and antiferromagnetic phases now splits into two regions, chiral phase and ferromagnetic phase. So that's the message here. And instead of conclusions, I have a list of open questions. Basically, this talk, instead of like giving many answers, it kind of opens up more questions. In particular, so far in the literature, all known symmetry enriched conformal field theories, these phases are believed to be connected to the so-called symmetry protected topological phases, which are gapless. Okay, so whether this chiral Heisenberg phase is symmetry protected topological is an open question. We don't know that. What is the universal nature of CFT, the chiral Heisenberg criticality, as I mentioned? This we don't know. What is the nature of transition? It's a Lifshitz transition probably, but again, what are the correlations of this transition and so on? This is all not known. So it's an open question. So we added this chirality term to the Heisenberg Hamiltonian explicitly breaking time reversal symmetry because this triple spin product breaks time reversal symmetry. So this opens up a question whether one can add a similar term which preserves time reversal symmetry, however, leading to this chiral phase. And the answer, this is unpublished result, but my preliminary answer is yes. There are like a family of operators that preserve time reversal symmetry, giving rise to this chiral ground state, chiral Heisenberg ground state. Okay. So if there are some material supporting chiral interaction, this is also an open question. How to realize chiral interaction with ultra quadratics? I have no idea, but there are some ideas. Maybe if people are interested, that would be a very nice project. How to measure chiral phase? Suppose we have this quantum material with this chiral interaction. How to measure chirality? This is something I'm very interested in to understand, but this is an open question. And so what are the non-equilibrium properties in terms of like transport at high temperatures of open systems? So this is also all kind of unknown. Okay. So thank you very much for your attention.
Questions? Yeah. So for the first point, did it take something like entanglement spectrum to see if there is double degeneracy or something like that to take the SPD?
So for finite size systems, that's kind of, there is no.
But so, I mean, it's possible, for example, in Allen or that to see the entire entanglement spectrum region.
I know, yeah, it's possible we didn't do that.
Okay.
One needs to do careful finite size
Yeah.
scaling analysis.
And can you go to one slide, like the last slide? If I want to maintain the integrability with delta not equal to 1, how ugly is the last term? So the chiral term. No, in your Hamiltonian,
Yeah.
the first top one.
How this
ugly is
transforms
that
for
term?
XYZ.
Yeah.
Well, it becomes non-isotropic. It's basically, it's not ugly.
Okay.
It's just, yeah, I can write it down. It's pretty nice actually.
Question. So the story in 2D typically take Heisenberg, you add this chiral term, and you push into a chiral phase. Here it seems like the opposite story. Like there's just, you need a lot.
Yeah.
So it's not very sensitive. Right. Is that your sense?
So basically, this is our definition.
Yeah.
In that kind of schematic story, it's a little bit different. So I was doing chiral spoon liquids in 2D, and what we saw that in 2D when you're, so if you're doing DMRG, for example, one needs to break an universal symmetry by hand to increase the field strength. When this, if you're adding a seed, an universal breaking seed in an anti-ferromagnetic phase, nothing is happening, right? If you do a seed in a parasymmetric phase, it picks up singularly, it gives some interesting things, right? So that was the question. Okay, you introduce the seed in anti-ferromagnetic phase, nothing happening. And this was the idea. If you increase the seed, it becomes substantial. Will you still get to the chiral phase? And this answers that question. Yes.
Okay,
You will.
eventually.
But eventually,
That's correct.
but the ground state is still high.
Yes, so I think simple statement number simple. The point we realized that in reason recognition, we want to speak that we understand these state, right? Rapid strength in the and the strength will have a kind of interaction that we can continue. Most likely, it will connect This will be kind of moves, kind of smoothly throughout these features. I think it will be a continued work. That's a very, this is the system that.
Yeah, this is fantastic. Yeah, I'm very interested in it.
Okay, for the second time, we have to move on to, I need more to do, so let's, thank you. I did include it, because. So keep going, zoom. I see. Maybe this one. You just share your screen. Can people on Zoom hear me? Yeah. Okay, next talk, John's going to talk about non-equilibrium light-induced coherence. So he has about 30 minutes, and then try and keep it limited. And this is a full tech pointer. Let's see if my book actually works. Oh, you have a high tech. It's working. All right. Thanks for the introduction, and thanks to the organizers for inviting me. Today I want to tell you about work I have done a few years ago, and I took with me now as a faculty member at Yale on light-induced coherence. So this type, so is intentionally generic. I will define what I mean. Before I do this, I want to refer you to the publications. I wrote a paper in Nature Computation in 2021, and recently there's a paper just appearing in Now Letters in 2024. Doesn't even have journal number or any details yet. I'd like to acknowledge that my collaborators, precisely Andy Mills and David Reitman, and Duncan Canis and Benedict Kloss, and LMU
here's an outline of what I want to do. So by light-induced coherence, I'm thinking about the experiments, the so-called quantum probe experiments of quantum materials, in which you have light. Usually this is some classical light, like a displacement field, and will excite specific excitations of the crystal. And then we will get transient non-equilibrium behavior, and then a probe will come later on and probe what's going on. And I will discuss specific experiments that will involve nonlinearities. I have in mind exciting phonons in the crystal. That's very important. And I will discuss two regimes, fast phonons and slow phonons. So a fast introduction about these experiments. You don't need this introduction, but in a cartoonish way, really what I have in mind is crystals which have vibrations. These could be local vibrations, like intramolecular vibrations or intermolecular vibrations. And then the pump pulse will come resonant with the vibrations. The experiments I will discuss, these pump pulses are resonant with intramolecular vibrations. They excite those vibrations to very high amplitude that you could not do thermodynamically. So they induce a quench in the system, and then those phonons, which are coupled to the electrons, relax. They excite the electrons, and then you get something in the transient that could be interesting. For example, people have discussed possibilities of metal to superconductor transition or other sort of.
Those are molecular crystals, and you excite vibration inside every molecule.
Correct.
All of them.
Yes. Exactly. And then ultimately you need to measure what's going on. So you probe with whatever technique you're interested in, like with optics, for example, I could detect that transient state. Of course, interpreting these experiments is non-trivial. Here in mind, I have one specific experiment that excited a lot of people and also created some discussion in the community, where the authors of this work, this is the Cavallari group in Hamburg, it was led by Matteo Maturano when he was a student. They studied K3C60, which is a molecular superconductor, and they observed the possibility of a metal to a superconductor transition at high temperature. So let me tell you what they saw here. I don't want to get into a lot of details, but this is sigma 2, the imaginary part of the optical conductivity. And on this side, on this panel, you just see a typical experiment of sigma 2 as a very temperature at equilibrium. Nothing exotic about this. And
this is energy of light horizontally. What on the axis?
This is frequency or energy, and this is sigma 2, the imaginary part of the optical conductivity. Okay, so the red line is the measurement above TC. TC in this material is around 20 Kelvin. So above TC, the material is known to be metallic, so you get this red line. And then below TC, which is around 20 Kelvin, you do the same experiment, you get this divergence or quasi-divergence, your zero frequency, which indicates the fraction of the material that is superconducting. Right, so this is a standard experiment, nothing super crazy here. This is equilibrium varying temperature. What they have done is they took the material at 100 Kelvin, they repeat the measurement one time, so you get the red line again at 100 Kelvin, as expected. This 100 Kelvin is larger than 20 Kelvin, which is TC, for which the material is metallic. But then they repeat the experiment and they pump. And they get the blue line. And when they get the blue line, you see that the blue line at 100 Kelvin with pumping mimics the blue line at below TC, suggesting, if you believe this, the similarity to the induction of superconducting behavior, but now this is happening at high temperature via optical pump, right? So you could raise all sorts of questions about interpretation. I don't want to get into the experiment. This is not my concern. This is why I'm interested in this problem. This is a very interesting problem, and there's a plethora of works that appeared in the early times trying to understand, is it possible that light can induce superconductivity in a metal? What about thermalization? All sorts of things. But I'm going to take a more pedagogical approach or more bottom-up approach, where I want to simplify the problem into a simplified model that at least I believe has the necessary ingredients. I will start from 1D, so I'll show you 1D model of a metal. So please don't take what I'm saying to imply that I'm studying K3C60, that's the path down the line. However, I'm going to use an approximation-free method, which is an FES-based method. So I will be able to tell you what I know with sufficient precision. Okay? So this is the program. We want to start from all dimensions. Everything I will tell you about, you today is going to be in 1D, but the program is to do 1D, which is basically done, and we're finishing up, and then 2 ladders, and sort of program that people have done in equilibrium already. So that takes me to the model. How do you model this problem? And a very simple way to model this problem, the model actually, there's also discussion in the literature what's the right model, but at least I think everyone agrees on these ingredients. The light electric is an electric field that excites IR phonons. So these are dipole active phonons. So when they are excited, they are like dipoles. And K360 has a center of inversion. So those two things together imply that there's some sort of nonlinearity. I think everyone agrees on this. By that, I mean the following. If you're exciting a dipole and your Hamiltonian is invariant under inversion, because K360 has center of inversion, then the dipole cannot be appearing linearly in your Hamiltonian, right? It has to be nonlinear. And there are multiple ways. One plausible and probably dominant way that this could happen is that your dipoles, which are the phonons, the IR phonons, appear to leading order quadratically in your Hamiltonian and coupled to the electron density.
So C are electrons, X are phonons.
Correct. So this is creation operator for electron on site I or unit site I, and this is the dissonation operator for the electron. So this is the density, the unit cell I, and X is the displacement operator, the phonon that is excited by light in the unit cell.
I is what the index irons, atoms,
Sites.
sites.
But it could be atoms in like a boring crystal. Okay, so yes, I'm going to study a simple model, which is an extension of classical pillar textbook models. I'm not going to downfold from materials, though I claim that downfolding from materials is possible. And this is something I'm discussing with Mitterrand because he actually studies low-dimensional systems that we can do DFT4 and down. Okay, so let me be more precise. Here's the Hamiltonian. I have the normal hopping, nearest neighbor hopping, and if I'm finding, I'm going to call it J, so I don't confuse you when I talk about temperature, or if I talk about temperature. I have Einstein phonons. These are just local vibrations, and then they couple by JQ, Q for quadratic coupling, where the phonons nanosecond quantized using these bosonic creation ionization operators couple quadratically to the density.
What's the role of optics? Just producing some density.
It's coming. So now this is the Hamiltonian, but actually the light is a classical field. So basically the thumb field or the light field is a displacement operator that acts uniformly everywhere on the crystal and displaces the initial state of the phonons, which is the vacuum, to a new state, which if you know from optics, this will be a coherent state. So basically.
But you said it's vibration of molecules, but now you know displacement of molecules, right?
No. I'm saying what happens in the experiment. I'm going to study a model. Okay. And then in this model, everything is local.
So here, light is displacement, cause displacement of atoms,
So
not creation of electrons.
No, light doesn't do anything to electrons. Light goes and creates a coherent state of the phonons on every side. So basically, if you took this Hamiltonian, you obtain the ground state and you time evolve, you'll get nothing interesting because it's already an eigenstate. What I'm trying to do is I'm trying to take something that's close to the ground state of the fermions, but I'm changing the phononic sector dramatically by creating a coherent state, a product state of coherent states, each one on every site in phase. Each site has a coherent state.
It's like K0 phonon, like all the letters are the same, or it's a modulated.
No, it
it's
just
a
means
light
that-
wavelength.
Yeah, it just means exactly. The light wave is long wavelength, so it excites everything uniformly in the crystal into a coherent state. And then the strength of the excitation tells you on average how many phonons you excite in that coherent state. Coherent state locally has a Poisson distribution, and so the mean of that distribution is controlled by the intensity of the light field, okay, which is this parameter alpha.
So you're adding energy to the system, but you don't have any way to take it out in your model.
No.
So unlike maybe in the experiment, there might be dissipation, some equilibration, but here it's stuck.
Yeah, but that's a very good question. That's true. But I'm interested in the transient. So that's where I'm going to keep my mind at. I am also interested in thermalization, but I can tell you that it's pretty darn hard to get anything useful about thermalization here. I can tell you what we know, but I'm doubtful that it's true. Okay?
Could you please, excuse me, interrupting, describe the protocol? It's just a pulse and then during some time you observe something or what?
So what you were asking me about the protocol I2 in
Whatever. So
Yes.
what do you have in mind? Because you will be doing something to your Hamiltonian.
Okay, good, very good. So I take this model with JQ very small. Okay, that's actually what's realistic, but the non-linearities are small. But compute the ground state of that thing, okay? As a side note, the overlap of that ground state of that thing is very large with the free fermion ground state. Like I computed that numerically. So basically, I'm telling you the ground state is free fermions equilibrium. Then I implement an operator that is the product of this thing with the index I, which is the site index. So I basically applying these operators all at the same time on every site to excite the form. This operator is a coherent state operator, doesn't know anything about the electrons, excites the forms. And then I just do time evolution. It's no longer an eigenstate.
So just initial state.
Yes, it's no longer an eigenstate. So and that's what happens in the experiment. You have an ultra impulsive excitation and you let it go.
Shift problem.
Okay, and then I compute 2-point correlation functions. Equal time 2-point correlation functions.
Essentially, you will be exploring time evolution.
Exactly. Okay, unfortunately, it's very hard. I'd love to do it and we have ideas for doing it, but it's very hard to compute different time correlation functions that will get us optical conductivity. Then we can go and like be more brave and prepare the experiment.
Of the problem is time evolution.
Time evolution. Okay, good. So I want to highlight, and this is not to say that this is not good, but like in the 2017 paper, the activity that was done is to write the model and do a 2-site study of exactly what I just told you, but 2 sites, right? So basically in the study, they access what could happen locally, but you have no idea about long-range coherence, right? Because you cannot infer long-range coherence from 2 sites. That's precisely why my title is like induced coherence or like thereof. So now I get to the first section on results. That's the 2021 results, the fast phonons. So actually, these are not super fast. They're actually slow. The reason I call them now fast is in retrospect. The phonon frequency is j pi over 2. So pi is like 3, roughly 3.1 something, and over 2. So that's like 1.5 times j. And the reason I chose that is at the time I did TEVD, time evolved block summation. For those who don't know what that is, it's just a tensor network method that is supposed to be numerically exact. I did the infinite version, but I did the vanilla approach, meaning I treated the local Hilbert space dimension composed of the electrons and the phonons without using any tricks. I just took the model and I studied the same way people study XXZ models, electronic models, and whatever. Of course, this is very hard because there are 12 phonons per site and 4 electrons per site. The local Hilbert space dimension is 4 times 12. So that's hard. That's why I couldn't go to lower phonon frequency. Because if I go to lower phonon frequency, I basically will simulate 1 times 10. I'll get no useful information. And now we can do better than this. But anyways, at the time, that's what we did. And then I used a confluence alpha equal root 2. To remind you, this confluence is the intensity of the pulse. Alpha equal root 2 means I excite on average 2 phonons per site. And that's important because we don't want to excite too strongly, because then you would thermalize very quickly. You want to hopefully excite something, and the coupling, the nonlinear coupling is small, and you hope to see some interesting phenomena out of it. Okay, so that's what I have done, and we did 2 things. We did ITVD, the tensor network approach, that's exact, but you can only go to time 5 in inverse of J, in the inverse of the hopping, so 5 hops. But then you can say, well, you know, John, there are other things you need to know about what happens in the long time limit. So we complement this by doing Krylov propagation, or if you don't know what Krylov propagation is, like essentially exact diagonalization, an efficient form of exact diagonalization. But of course, the price we pay is we can't do only very small sizes. We did 6 sites. So here I can assist thermalization, and actually found no thermalization in the infinite time limit, but it's 6 sites. So maybe you shouldn't believe me. Okay. And so for this talk, the goal is to make exact statements about the intermediate to long time dynamical behavior, which is in the order of the transient, like 5J, or order 1 in J, not so large in J, that is beyond what is found in 2-site studies, beyond the 2-site exact diagonalization. So here's the main result. These are the dynamics of 2-point correlation functions. Here I show you 3 types of correlation functions. C of K, that's the charge response or the charge density wave retransformed, in K, the momentum. S of K, the spin response, and P of K, the pairing response. So those are the 3 plots.
So what are on horizontal axis?
Yes, I'm getting there. So on each one, you have the Z axis, that's the correlator, and on X, the momentum. So I have full momentum resolution because I'm doing an infinite form of tensor networks, and I have time. Okay, time is parameterized in some way, it doesn't matter, but basically I can go to find time 5 in units of 1/g. These subplots are just cuts of the peaks. So this cut in the peak is shown here, and I vary the electron phonon coupling. This cut is shown there with the same variation of electron phonon coupling, and then I have two cuts for pairing at 0 and at pi, because this is interesting to look at pairing at pi because of possibilities of pair density waves and so on, and also the two cuts as a function of electron phonon. What I want you to observe is, so let me first note that charge correlations at 0 momentum as a function of time don't change because that corresponds to conservation of density. So this is stuck, that cannot change. Same for spin. Conservation of spin imposes conservation of the spin time evolution at momentum 0. However, if you look at everything, what you basically see, aside from a lot of mess, is that things are flattening in momentum space. So this flattening in momentum space, we took it to be an indication that there's some form of disordering or loss of phase coherence that is happening in the course of time evolution. Okay, and how do you understand this? So, this is a hypothesis. I will show you some analytical theory that will explain it. You will still be doubtful, then I will show you some numerics, and I hope then you will be convinced. So the idea is to try to actually look at that model and see if we can learn something from that model by playing with it. We could have wanted to do perturbation theory, but we don't have a clearly perturbative way of dealing with this. So what we did, the idea was first presented by Dante, but there are certain things that Dante and collaborators did not really observe. The idea is if you took this Hamiltonian, I'm going to go a few slides back, just to remind you quickly of the Hamiltonian. Here, the usual electron phonon Hamiltonian is linear. If I expand that thing, I get bi dagger squared, b squared, and bi dagger b. Bi dagger b, we're fine with. We know how to live with. Bi dagger squared, we don't know. B squared, we don't know. But we're lucky, Bogoliubov exists. And Bogoliubov has taught us how to get rid of these, terms that are squared. So we can eliminate them. We do what is called a squeezing transformation. It is squeezing because actually if you go carefully through the derivation, to eliminate them, the transformation has to depend on those two operators and the density. It will be like Koch and Cinch of B dagger and B parameterized by the electron density, okay, which makes it an unusual case. But that induces these types of unusual interactions when you eliminate those terms and you write linear combinations of them in terms of new operators, new bosonic operators, the betas. You get another Hamiltonian where the electron hopping is normalized to J star. The phonon hopping, the phonon energy scale is normalized to omega star, it softens, and then you get those interaction terms. Density of the electron couples to the density of those new squeezed bosons, and a minus U Hubbard term that couples to density of bosons. The nice and important observation on this is that these beta operators are classical. They are conserved at all times. They commute with every term in the Hamiltonian, and hence they commute with the Hamiltonian. So
this is an exact UV transformation, right?
No, this.
Or there are higher terms in N's.
Yeah, so you can start with the transformation, but then there will be some messy term, and then you get, and when you do the transformation, you find a small parameter, you tailor expand, and to order.
So it's low electron density approximation.
No. This coupling over omega is
okay,
small.
no coupling.
But we're happy because actually the coupling we use numerically is small, and the model for other experts in the audience, they will know this. The model has a stability issue. The coupling cannot be very large. The model becomes unstable if the coupling is large. I don't want to get into the discussion now, but happy to tell you one-on-one. But the point is, this is not a clear small parameter. When I do the transformation itself will have a square root of 1 plus this small parameter. Then I expand. After I do the transformation, I get this model. Okay. Then you will tell me if you work with type evolution problems, you'll tell me, John, but you can't understand anything in this Hamiltonian because you need to transform the initial state and transform the operator you're looking at. So that's indeed what we do. But the leading order in the small parameter, the initial state and the observables we're interested in, like charge density correlations or spin density correlations, are untransformed. So basically, the statement of the problem is that I can think of the original problem that I simulated brute force numerically with, these highly compressible states, MPS states, as an effective problem described by this Hamiltonian, but with the same initial state and with the same observables. And now I have two frames, the leading order in G over omega, I can compare in those two frames. Okay? So what can we learn? Before I tell you the comparison, which I have done numerically, what do we learn from this Hamiltonian? Well, I told you a few slides ago that these new bosons, the squeezed bosons, are in this approximation are conserved to all time. So basically, whenever you're computing an observable at any time, it's like you're doing an integral over the wave functions, and these wave functions have a classical part that's a classical probability distribution. You can actually formally show that if you take an observable and you compute it, you are averaging over different squeezed boson occupations, and that is formally exact and formally exactly equal to a problem in which you do the Anderson disordered problem, where you have an electron in a random potential, and you take different values of the potential and you average. This averaging here is happening self-averaging in the course of the dynamics. In the Anderson problem, it happens because you take a small part of the system, and instead of it self-averaging over very large scales, you sample over different organizations and average. So we verified that numerically, but actually, other colleagues have worked on this problem. They call it the problem of disorder-free localization. They study it in the context of lattice gauge theories, which are different from our model, but structurally have some similarity. There's a local symmetry from the gauge sector, and these are local bosons, the two bosons most of the time. It can also be U1, but that's a little more tricky. And they couple two fermions, and they have shown that at least if you have no interactions, you can think about this as some form of disorder-free localization that mimics Anderson localization. So I told you a lot of things, but you still should be doubtful. Here's the only thing that gives me some confidence. So I actually went and I simulated the exact model, which I already showed you some results for, and this effective model under the approximations and claims I gave you. So here are the results. I simulated both with TEBD, with the tensor network approach. So these are exact results for both models. The only approximation is in the derivation of the approximate model. And this is time averaged results for the double occupancy, local double occupancy, the charge density correlations of momentum pi that corresponds to charge density waves or staggered charge densities, and spin density wave at pi, which is the staggered spin density. The different lines with different colors are different values of coupling, going from 1/4 to 1/16, right? So the first exciting thing is even for 1/16, you're still getting something. If you try to do this at equilibrium, you see no difference. If you study the properties of the model at equilibrium compared to free fermions, you see no difference for free fermions. So that just means that there's induction of strong coupling behavior occurring in the course of the dynamics. The second thing is, at least qualitatively and sometimes even semi-quantitatively, this effective model, dash line, is capturing what's going on in the exact model. So maybe you could believe what I'm telling you. Okay, so I got these results. We published them in Nature Communication 2021. Here's the summary of this part. But after we've done this, you sort of kind of, depressed. Or like, okay, maybe there's whole business of like reduced superconductivity, but there's no hope. I integrated the most brute force thing I could do, and I suffered to learn all this, and I'm not getting anything interesting. And this is because basically there's a form of dynamic disorder, even though the pump and the system themselves are not disordered, that induce some limited coherence. The coherence is very low. So I have enhancement of double occupancy. You already saw that here. I didn't highlight it. The double occupancy increases from the initial value, but there's no long range phase coherence. There's no, superconductivity or charge density over anything. But then I was interested in methodological developments, and I figured with collaborators a new way to deal with this problem when the phonorams are slow. And I thought, why not? It's just going to be a method space. So this is what I'm going to tell you about now. I'm going to be very brief. This is in work in progress, and I'm not ready to tell you all the details, but I'll tell you what I'm comfortable with. So now we can do phonome frequencies as small as j pi over 10. Again, pi is roughly 3, so that's 0.3 in J. This is considered roughly the state of art for what you can reach for the phonon energy scales with numerics. We can go to times that are twice the times I showed you. So not only it's lower frequency, it's longer. How do we do this? We don't use vanilla MPS anymore. We use an idea from purification. I will not get into the details, but those who are interested, happy to tell you, we basically take the original problem and we double the Hilbert space to have the original boson and fictitious bosons that correspond to a bath, and we impose conservation of total boson number in this space, and then we project back on a Hamiltonian that isomorphic with the original Hamiltonian. This is an exact process, but the gain is when you simulate this thing, and then you project, that thing has U1 symmetry. You can parallelize for MPS folks. You can parallelize in different U1 sectors, and then you do two things. You do the usual one-dimensional truncation, and you compute the global phonon density matrix, and you truncate in that as well. So you dynamically optimize the phonons in the dynamics, and that's why we can study things as big as 60 phonons locally. And we check conversions of these things. Here I show you some results. So we already wrote a paper in our letters, but here about the methodology and about some tomography and experiments. Here are new results that are not published yet about the charge density correlations at momentum as a function of momentum and time and the parent correlations. When the phonon frequency is lower, as in this plot, as opposed to what you saw before, the flattening is gone. There's no longer flattening. In fact, pairing looks like it's oscillating and maybe increasing a little bit, and charge looks like it's growing, especially at pi, the one that we care about, the staggered density, charge density wave correlations, and maybe it's going to blow up as we go longer to time. We couldn't simulate longer in time. And now we looked at the charge correlation function in real space. This is on a log scale. Unfortunately, we're not doing the infinite version of MPS. We're using the finite version, so we can't resolve everything yet, but it does look like there's something that's going on here. It's not, at later times, the darker blue colors, it doesn't look like it's exponentially decaying. So, that is suggestive, that's what I'm comfortable to tell you right now, suggestive that there is a form of light-induced long-range phase coherence that happens when the phonons are very slow. Here's a comparison between the solid and dashed lines for the charge density wave correlations at pi between the exact model, the solid lines, and the effective model. On the left, you have the exact data for the dynamics. On the right is time average. And you see, the effective model is not doing an amazing job. We have better data now, but it's capturing things. If you follow the green line, it has the same qualitative profile. The blue line, the same qualitative profile. So we can use the effective model to understand what's going on. And I think I understand now what's happening, but for the purpose of time, what's happening with regards to why reducing the phonon energy scale helps. But for the purpose of time, I don't want to get into details now, but happy to discuss with you. But the upshot is there's evidence that there's light-induced enhancement of long-range phase coherence. Perhaps it's not yet sufficient to break the symmetry and get us a superconductor charge density wave, but it's optimistic from a controlled method, and it opens the door for interesting things in higher dimensions. So here's my summary. They're basically two distinct regimes, fast phonons and slow phonons, and we see that this order is playing, dynamically induced disorder is playing an important role in stabilizing short versus long phase coherence. Thank you. I want to acknowledge my collaborators and the Air Force funding.
We have time for a couple questions.
Anything survives in a classical limit?
Classical of what?
Just assume that I would consider just classical electrons and a crystal with whatever density modulation and phonons. You can look at it as a local density modulation with medium, which would get translated into conductance modulation. Nothing survives, and this is all phase.
Yeah, so the only thing I don't understand from what you asked is what do you mean by classical electrons? Are they still hopping or they're not hopping? Or so that's the only part. I understand if you talk about classical phonons and classical modulation, but the electrons are still going to hop and they kind of distribute the energy in the crystal, right?
Okay, yeah,
and I think
if I impose the field, then so I would need to consider classical just conductors, just impose a big field and see if I would get these correlations in because of phonons.
Yeah, sorry, that question I don't know the answer to the question, to be honest.
I was curious to understand a bit more of what you understood about the role of these low phonons.
Yeah, good question, yeah. So, let me tell you how I understand it now. So I'm trying to find the model. So this is the model. And the way I understand it now is, so we have better data now in which we, at slow phonons, we simulate the effective model and the exact model and they match semi-quantitatively. The way I understand it now is I told you that this is a distribution over different phonon numbers and the dynamics is self-averaging over them. If I take the phonon frequency to be very small, it means I'm exciting everything at one phonon state. If I think about this as a disorder state and I do the Anderson or the Fermi-Goldman argument about how I destabilize an Anderson localized state, that perturbative argument tells you one localized state, another localized state, they couple with a matrix element, and in the denominator is the energy difference. But the energy difference depends on the phonon energy, and the phonon energy is now gone to zero. So that term diverges, destabilizing that disordered state. So that's my understanding of what's happening. In other words, there's actually a distribution of finite phonon energy that I'm averaging on, but when the phonon energy scale goes to zero, it's like a delta function, right? So, one goes on, right? So the disorder, so there's no really averaging anymore. There's no really disorder anymore. So that's what was missed in the previous works, is that the disorder is not only controlled by that term, which looks like a density coupling to the fluctuations of the bosons, it's also controlled by the frequency, the energy scale of the bosons. Does that make sense?
Can you tune this? So can you?
Not that I maybe pulled atoms, but we're not after pulled atoms, right? So experimentally, the slow phonons are the more realistic regime because the phonons come from the ions, and ions are very heavy, electrons are very light, so the phonon frequency is proportional to 1 over root m, the mass of the ions, the phonon frequency will be very small. So that just means that actually one may now be a little optimistic about possibilities of likely induced long-range phase clearance.
Intuitively from that, there's more phonons with it. It seems like there's an attractive, that's why I'm expect more pairing, but I'm sure it's not.
Yeah, it's a great point. So the excitement in the beginning of 2017 paper, which was a two-step study, was focused on this pairing. So indeed, the double occupancy increases, we saw in the numerics. But the question that people didn't really pay a lot of attention to was, well, I mean, it can increase locally, but you have long-range phase coherence, and that seems to be, there's an interplay between disorder and what's going on, and then the third axis, which we're going to talk about much, is thermalization, right? If things are heating up, then they're going to lose also coherence. On the transient scales I discussed, there's no heating up. I didn't show the proofs, but that's the case. Does that make sense? More sense now?
Yeah.
Oh, there's another point too, that maybe that's also nice, that at half, this is at half filling, and at least from standard, attractive overview model with 1D and half filling at equilibrium, CDW and superconductivity are degenerate. So you may see in the end that charge density is growing, but I'm actually celebrating because I'm happy. I don't care that it's growing and not pairing is not growing because I'm a very special point to understand pairing better. You're going to do
Good, all right, let's sing again. Good. All right, our next speaker, Alexei's going to tell us, he's our last speaker, about the Kondo lattice models.
Thank you very much for staying to the bitter end. I'm very grateful to the organizers, to Tole and Vadim for giving me this opportunity to talk. So I will tell you about some, I think, very interesting model which has two merits, at least two. The first merit is extremely rich in physical properties, because you will see here exotic superconductivity, pair density wave, odd frequency pairing, spin liquids, so confinement with a extremely long confinement values, fractionalization, everything in one package. And another merit, it is basically tractable. Well, I'm reluctant to say exactly solvable because usually we use this term exact solutions in the context of the Beth ansatz. Well, it is not solvable in that sense. And I acknowledge my collaborators, Piers Coleman, Aditya Panigrahi, and Tole, who is here. So, the model I will be talking about is a version of a Kondo lattice. So what are Kondo lattices? It is when itinerant electrons coexist with local models. And then the standard wisdom is that you can have two phases when the interaction between the local moments overcome the exchange with the electrons, then some kind of magnetic order will occur, or probably a spin liquid phase. And in the opposite limit, when the Kondo screening overcomes the direct exchange or Archiquet exchange, then we will have a heavy fermion Fermi. Here I will consider a more exotic possibility when the spin subsystem is a liquid with fractionalized excitations. It will be a generalization of the Kitaev spin liquid, the so-called Yauli spin liquid. And the corresponding Kondo lattice model will allow analytical treatment. And the phase diagram, so basically the novelty is that between
What up on the axis? What up on the axis? Temperature and what is
J is the exchange, J is the exchange, the Kondo exchange interaction between electrons and localized modes. So, but basically, it will when this interaction is ferromagnetic, then spins decouple from the electrons, and we have a situation of the so-called small Fermi surface, when the Fermi surface is formed by the electrons, and when the exchange is large, we will go either to a Kondo insulator if the electron band is half-filled, or into a heavy fermion metal if it is not, but in between it turns out there is an exotic phase, this exotic superconducting phase with a charge E condensate. And I forgot to tell you that the quantum model I consider is three-dimensional. Three-dimensional. That's another merit of this. Yeah.
Are you considering single channel and the spin half or?
Yes, spin half single channel. Yeah. Now, it is all closely related. This exotic superconducting phase have something which we call fractionalized order, and the concept of this order is that when electrons create bound states with fractionalized excitations, and this, but if these fractionalized excitations happen to be fermions, as it will be in the present case, then these bound states can condense, and that's fractionalized order. And in the current example, it will be a condensation of spin 1/2 charge E bosons, because my fractionalized excitations will be spin 1 neutral Majorana fermions. It will be bound states between this Majoranas and electrons which can get.
For uninitiated spin half bosons, what it requires for a system?
I will show you the model. The plan for the talk is that, well, our model is quantum lattice, itinerant electrons interact with localized moments. The spins interact between themselves, forming the so-called Pauli spin liquid. I will explain what it is. This spin liquid is solvable for any lattice with coordination number 3. And it is an SU2 generalization of the famous K-type spin liquid with some important modification. And we found three-dimensional solvable example of such quantum model and displays rich physics, including pair-density wave, odd frequency pairing, and quasi-fractionalized order, anomalously long confinement radius for charge in orders. And the results in a nutshell. So the essential ingredient here is the Pauli spin liquid, and it is a spin liquid where excitations are neutral spin 1 Majorana fermions. And the physical spin operator is expressed as a bilinear of this Majorana fermions. And due to the quantum exchange interactions, itinerant electrons create bound states with this Majorana fermion, and such a bound state of object of spin 1/2, which is an electron, and spin 1, first of all, of two fermions is a boson, and it carries spin isotopic spin 1/2. And since it's a boson, can. Now, what is the Yaoli model? This is a Hamiltonian. At each side, there is spin 1/2 and orbital the degree of freedom, which is also spin 1/2. And the exchange between the spins, which are sigma, is like the Heisenberg one, but it is decorated by the Kitaev exchange. So this means that if I look at this lattice, for example, along the green line, it will be tau x, along the blue, it will be tau y, and along the brown, it is tau z. And we look at this very strange particular lattice, which is called hyperoctagon. And why we look at this? Because it turns out that the excitations of this model, which are Majorana-Fermions, will have a Fermi series. It's a rather unique lattice where excitations of the spin liquid have a Fermi series. Now let me explain how you solve this. It turns out that you can fulfill all commutation relations of Pauli matrices sigma and tau by writing them down as bilinears of Majorana-Fermions. So Majorana-Fermions are real Fermions, so psi dagger is equal to psi. If you impose this constraint that all the product of all 6 of them is equal to 1, this constraint commutes with the Yauli Hamiltonian, then you will see that the product of sigmas and taus is actually fermionic bilinear. And you substitute it back into this Hamiltonian. And you obtain you obtain something similar to the Kitaev model, but with 3 Majoranas instead of 1 on each link. There is Z2 gauge field, which is static, which commutes with the Hamiltonian. So therefore, the excitations of this model are this propagating Majoranas and static fluxes of the Z2 field. To create such a flux, you need a finite energy because the electrons don't like to live in a non-uniform field, and there is a characteristic temperature the below which the Yauli model goes into a phase with rare Z2 fluxes, and in the first approximation, you can just treat this gauge field as a constant and get free Fermions. And lo and behold, if you diagonalize the corresponding matrix, you will get Fermi surface centered at a particular point in the Brillouin zone. Why there is nothing on that side? Because Majorana fermions are like ordinary ones, but for half of the Brillouin zone. In momentum space, you can introduce creation and annihilation, operate the Fourier components with, say, with negative k, will be creation of operators, components with positive k, annihilation. Now, the most difficult step is taken. Now we add electrons, putting them on the same lattice with nearest neighbor copying. Conda exchange between sigma spins and electrons, and this conda exchange can be decoupled by the Hubbard-Stratonovich transformation, and you see this Hubbard-Stratonovich field is a spinor, is a charged spinor, and this will be an order parameter. Now, we first, the easiest problem is when the electron band is half filled, and then the Fermi surface of the electrons will be exactly like the Fermi surface of the Majorana one. There will be two Fermi surfaces. Sorry, but the only difference is that it will be centered at the gamma pole. So in this case, we have a nesting, like for a Peierls phenomenon, and the Majorana fermion bubble will logarithmically diverge. And then we have a situation similar to what we have for BECS theory. In order to generate instability in the pairing susceptibility, you just sum up bubble diagrams and get this condition. So TC will be logarithmically, we will be an exponent of the inverse Conda exchange. Now, what happens if you dope the system away from half filling, then you can the electron forming surface will shrink or expand depending on the doping, and the nesting will no longer be there, and eventually sufficiently large large doping, the instability will disappear. But there will be some interval where this superconducting instability will still survive, and then there will be an interval similar to FFLO state, because you can show that the chemical potential here acts as Zeeman field for the superconductor. So what kind of superconducting state we have for half field? There is some topological property here, because Dirac electrons with spin 1/2 is like 4 Majorana fermions, and they have to couple to 3 Majoranas, so there is a mismatch between the degrees of freedom, and 1 Majorana from the band will be left unaffected. So it means that in this superconducting state will have a neutral fermionic mode. It will be like a thermal metal. Now, what? Now let's take a look at the conduction electron self-energy. This V, as I told you, this is an order parameter, this charged spinner. So electron couples to the spin liquid. Electron in the presence of this order parameter, electrons becomes a Majorana fermion, and then it can re-emerge as a whole. This is an anomalous part of the self energy, and that's how it looks like. For two spinners, you can arrange them into 3 mutually perpendicular vectors. So this superconductor is really a combination of a spin density wave and the triplet pair. But you see, it's fractionalized because this between V and V, there is a Majorana propagator here. So that's delta, the anomalous part of the free energy. You see, it has an odd frequency part. So odd frequency pairing, and this charge 2E object is made of two charge E spinors which are separated from each other in space and time. And it also turns out that due to the fact that electronic Fermi surface and spinel Fermi surface are centered at different parts of the brilliant zone, this vectors D oscillate B inside of the unit cell. So it is in that sense, it's a pair-based. Now, as I said, away from half filling, the nesting between electrons and Majorana is violated, and the chemical potential acts as a Zeeman field in a conventional superconductor. And following the standard logic, we conclude that Q0 superconductivity is unstable when the chemical potential exceeds the superconducting gap. So this exceeds the compensation rate. At high chemical potential, we may get bound states with finite momentum, like in FFLO superconductor. Now, this was all done in assumption that the excitations of the Z2 gauge field can be neglected. But we looked at the simplified version of this of the Ginzburg-Landau theory for this exotic superconductor. When instead of SU2 we have the U1 symmetry, and took into consideration the possibility that this static gauge fields are excited. This was done in collaboration with Anatoly, and it turns out that if you look at the gauge invariant correlation function of exponents of phi field, so the charge E, they apparently have a finite correlation there. For if kappa is not is finite, if it is infinite, of course the correlation is infinite as well. So, but it turns out that this correlation length in terms of the parameters of the model is large. I think this, for example, for tanh kappa for k equal tanh kappa here, well, on the boundary with a disordered phase, the correlation length will be already 12 lattice spaces. And for okay, point 2, which is here somewhere, we looked at this correlation length, and when you go further into the superconducting phase, it grows linearly with J. And again, it becomes well, from the order of 5 at the boundary, quickly becomes the order of 20. So therefore, the concept of fractionalized order still holds at intermediate distances for which are much larger than the lattice cluster. So I think I'm done. So the conclusions is that we have an analytically treatable convoluted model which describes a plethora of phenomena usually associated with strong correlations. All these phenomena, such as pair density wave formation, or frequency pairing, or the parameter fractionalization, are facilitated by the emerging gauge fields of the underlying spin wave.
Any more questions? I had a question about the pair density wave. So that's distinct from the, I missed this. So that's distinct from the fractionalized phase, or is it
Lower here, it is this
happening inside pair density wave? Or?
Well, yes, yes.
I see. So you have the pair, the density wave order pairing or fractionalization, same place, same time.
Yes.
I see. I missed that. I thought.
No. No, this exotic superconducting phase has all this similar thing.
You have a slide on bias.
Why is the excitation this fluxes of Z2H?
What is that in the context?
You see, this is the Yawli model. This is this Z2H. So if the fluxes are rare, they act as impurities. It's resonance scatters located at certain links of the waves. In the limit of zero temperature, there are simply no flux because the Weisel flux was state.
So if there's no more questions, let's thank him again.
thank all the speakers for coming. It was a great conference, great talks. Thank you again, everyone.
You guys been playing?